In precisely 2 days, an event of immense consequence will unfold. An object originating from beyond our solar system, traversing at a velocity of 137,000 miles per hour, is projected to make a close pass to Mars, a mere 18 million meters away. For the very first time, we will capture detailed imagery of this celestial visitor with an unprecedented level of clarity. However, the nature of this object is profoundly perplexing. Its estimated mass is 33 billion tons, placing it 3 to 5 orders of magnitude heavier than any previously detected interstellar body. Astonishingly, it exhibits no discernible tail, despite expelling 150 kilograms of material into space every second. Furthermore, any luminescence emanates forward, not backward. Its composition appears to be nickel devoid of iron, a departure from fundamental chemical principles, and its trajectory aligns with the plane of our solar system with a statistical likelihood of only 0.2%. Avi Loeb of Harvard University, the same researcher who investigated oumuamua, has assigned this entity a score of 6 out of 10 on his scale for technological artificiality, a significant rating, not a minor one. Concurrently, on Mars, NASA has released peer-reviewed findings substantiating the possibility of ancient life embedded within rocks exhibiting a spotted pattern. In the same week, HSBC pioneered the use of quantum computing in actual financial trading, achieving a 34% performance advantage over conventional systems. The release of GPT-5 instigated widespread user dissent, with many characterizing it as overly sanitized. Fusion energy achieved a sustained reaction for a remarkable 22 minutes, and China's carbon emissions saw a historic decline for the first time. It is October of the year 2025, and the pace of scientific advancement is so rapid that yesterday's groundbreaking discoveries have already become commonplace. Within the next 2 hours, we will connect all these seemingly disparate threads. From the interstellar anomaly approaching Mars in 48 hours to the potential life NASA has uncovered in ancient Martian sedimentary layers. From quantum computers entering the trading arena on Wall Street to artificial intelligence that users claim has lost its essence. From the revival of extinct species, specifically 12 distinct avian kinds, to medical breakthroughs conquering previously incurable ailments. Certain of these developments have been conspicuously absent from mainstream media coverage. Others have been reported without a full appreciation of their profound implications, and a select few are actively being suppressed. This is the compilation of scientific news that they do not wish for you to synthesize. Welcome to October 2025, a time when events are poised to become extraordinarily intriguing. If you are prepared to delve deeply, kindly activate the like button and subscribe. Then, share in the comments section your current location, the time in your area, and the most peculiar experience you have ever encountered. Let us commence. Chapter 1. Three-Eyed Atlas. Deciphering the Anomaly Secrets. Three-Eyed Atlas is now less than 48 hours from its closest proximity to Mars. If you have been following this unfolding narrative, you are aware of the anomalous forward-facing glow, an observation that defies conventional understanding. You are familiar with Avi Loeb's research highlighting the object's implausibly high mass. You have witnessed the cycle of speculation, debunking, and subsequent counter-debunking. However, what may still elude your grasp is the coordinated effort planned for October 3rd, when multiple spacecraft will simultaneously direct their imaging capabilities towards this object. The Mars Reconnaissance Orbiter, China's Tianwen-1, the European Space Agency's Mars Express, and the ExoMars Trace Gas Orbiter will all synchronize their operations to capture images with a resolution previously unattainable, specifically 30 kilometers per pixel. While this figure might not immediately impress, its significance lies in its capacity to enable us to distinguish the object's nucleus from its surrounding dust envelope. We will ascertain its precise shape, observe its surface characteristics, and determine whether its motion is controlled or erratic. What renders this particular moment exceptionally unusual is that the operational teams for these orbiters were not initially planning such an endeavor. The primary function of Mars orbiters is to study the planet itself, not to image distant interstellar objects millions of kilometers away. Yet, upon the scientific community's realization that Three-Eyed Atlas would pass within such a close range, making it amenable to clear imaging by planetary spacecraft, a swift mobilization ensued. Observation schedules were hastily revised, and instrument time, typically requiring months for approval, was reprioritized and granted within days. The urgency stems from the fleeting nature of this opportunity. Three-Eyed Atlas is traveling at interstellar velocities. Following its passage by Mars, it will continue its inward trajectory towards the Sun, reaching its perihelion on October 29th, after which it will vanish, propelled back into the cosmic void by the Sun's gravitational influence, accelerating away from us indefinitely. We have but one chance, one critical window, and that window opens in 2 days. Now, the latest data becomes paramount. 6 days ago, Loeb and his colleagues published a new paper, not a preliminary report or a blog post, but a rigorously peer-reviewed analysis that successfully navigated the stringent scientific review process. Its findings have fundamentally altered the discourse. The paper meticulously examined over 4,000 observations of three-eyed Atlas, gathered by 227 observatories globally between May 15th and September 23rd. Their objective was to identify a specific phenomenon, non-gravitational acceleration. When a comet approaches the Sun, its surface ice undergoes direct phase transition from solid to gas, a process known as sublimation. This expulsion of gas acts akin to minuscule rocket thrusters, subtly deflecting the comet from its predicted gravitational path. Every active comet ever studied exhibits this effect, a hallmark characteristic of cometary behavior. Three-eyed Atlas, however, displays no detectable non-gravitational acceleration whatsoever. Let that sink in. The James Webb Space Telescope has confirmed that this object is shedding approximately 150 kilograms of mass every single second, equating to 330 pounds of material being ejected into space every second. The outflow velocity of this material reaches 440 meters per second, nearly 1,000 miles per hour. This is not a marginal effect. It represents a substantial, continuous propulsive force that has been active for months. Yet, when plotting the trajectory of three-eyed Atlas with exceptional precision, utilizing thousands of observational data points, it adheres to a purely gravitational path. The residual acceleration, the deviation from what gravitational forces alone would dictate, is less than 15 meters per day squared. To provide perspective, this is approximately 100,000th of Earth's surface gravity, effectively negligible. How can such a significant, continuous propulsive force be exerted without yielding a measurable acceleration? There is but one conceivable explanation. The object must possess an extraordinarily immense mass. It must be so massive that the outward thrust, despite its considerable absolute magnitude, becomes insignificant when compared to the object's inertia. The calculation is straightforward. Given the observed rate of mass loss and the velocity of ejected material, the absence of measurable acceleration implies a minimum mass of 33 billion tons. 33 billion tons. This figure suggests a minimum diameter of 5 kilometers. Assuming a solid density, a 5-kilometer diameter is considerably smaller than initial estimates based on brightness, which suggested a diameter closer to 20 kilometers. Nevertheless, it remains substantial, residing at the upper limit of sizes observable by Hubble. Critically, it is 3 to 5 orders of magnitude more massive than oumuamua. This presents a conundrum for which no satisfactory answer has yet emerged. Where do interstellar objects weighing 33 billion tons originate? The cosmic abundance of heavy elements is finite. Rocky material, the fundamental component of planets and asteroids, must be ejected from planetary systems. Planets coalesce around stars, and as these systems evolve, gravitational interactions can expel material into interstellar space. This is the presumed origin of oumuamua and of 2I/Borisov. This constitutes the reservoir from which we draw our understanding. However, this reservoir adheres to a size distribution pattern. Smaller objects are prevalent, while larger objects are exceedingly rare, decreasing exponentially in frequency. Statistical analysis, a calculation meticulously performed by Loeb's team in their paper, indicates that the interstellar mass reservoir can only supply a 20-kilometer-sized rocky body to the inner solar system approximately once every 10,000 years. Even if we optimistically assume all available interstellar rocky material is consolidated into 20-kilometer chunks, a highly improbable scenario, the frequency remains one such object every 10,000 years. We have been actively searching for interstellar objects for less than a decade and have already encountered one. The probability of this occurring by random chance is vanishingly small, akin to winning the lottery on your very first ticket purchase. This leads us to consider less comfortable, yet plausible, hypotheses. Perhaps our assumed size distribution is inaccurate. Perhaps there exists a population of massive interstellar objects that deviates from the statistical norms derived from observing our own solar system. Perhaps three-eyed Atlas is not merely a chance fragment of ice and rock that has wandered into our vicinity. Perhaps it is something else entirely. Loeb assigns it a rating of 6 on his scale, a scale he devised specifically for such anomalous situations. A rating of 0 signifies a definitively natural origin, while a 10 indicates unequivocally artificial technology. A 6 suggests that the evidence is sufficiently compelling to warrant serious consideration of artificiality, yet not so overwhelming as to definitively exclude natural explanations. A 6 signifies a need for further data, which we are poised to receive in 2 days. The high-resolution camera aboard the Mars Reconnaissance Orbiter will capture images. If the nucleus exceeds 5 kilometers in diameter, and if its observed brightness primarily originates from a solid body rather than a diffuse dust cloud, then the natural explanation becomes untenable. It would be statistically impossible to aggregate such a mass within interstellar space and discover it on our third attempt at detection. The prevailing statistical models would collapse. Conversely, if the nucleus is small, with the majority of its luminosity emanating from an extended coma of gas and dust surrounding a modest core, then we are observing an unusual, albeit natural, comet. It would be peculiar, anomalous in its chemical makeup and lack of a visible tail, but ultimately explicable within the framework of known physics. Two potential outcomes, each carrying vastly different implications, and the definitive answer is expected on October 3rd. Now, let us examine the chemical composition, as this is where the situation becomes truly extraordinary. Multiple spectroscopic analyses have consistently confirmed the emission of nickel by three-eyed Atlas, not iron. In every natural astronomical object we have ever studied, nickel and iron are invariably found together. They share similar chemical properties, form under comparable conditions, and their presence is always detected concurrently in spectral analysis. While their ratios may vary, both elements are always present. Three-eyed Atlas, however, exhibits nickel in the absence of iron. The spectral data is unambiguous and clear. Nickel emission lines are evident, while iron lines are conspicuously absent. This is not a matter of iron being present below the threshold of detection. The instruments possess sufficient sensitivity. Were iron present in the expected ratios, it would be readily observable. It is not. There is no plausible natural explanation for this phenomenon. It is impossible to preferentially form nickel without iron through any known stellar nucleosynthesis process. Furthermore, they cannot be chemically separated post-formation due to their nearly identical behavior. Selective depletion of one element through sublimation or other surface processes is also unfeasible, as they sublime at similar temperatures. The chemistry simply does not align with natural processes. Yet, the observation persists: nickel without iron, a spectral signature that should not exist, stubbornly present across repeated observations. Then there is the trajectory. You have likely heard about its alignment with the ecliptic, the fact that three-eyed Atlas is traveling almost perfectly within the plane of the solar system's planets. This occurrence has a mere 0.2% probability, an unusual coincidence, though not entirely impossible. However, the trajectory possesses additional characteristics that compound these coincidences. The object's orbit brings it unusually close to Venus, Mars, and Jupiter, not to the degree of Earth's closest approaches, but closer than a random interstellar trajectory would typically permit. The minimum orbit intersection distance to Mars, representing the closest point three-eyed Atlas's path comes to Mars's entire orbital path, is a mere 2.7 million kilometers. This is approximately 7 times the Earth-Moon distance for an object originating from interstellar space on a trajectory established millions or billions of years ago. To pass this close to a planetary orbit represents an exceptionally precise fine-tuning. When these factors are considered collectively, the mass, the chemical anomaly, the trajectory, the lack of non-gravitational acceleration despite active outgassing, and the forward-facing glow instead of a trailing tail, each individual anomaly is peculiar. Some possess potential explanations, though these often necessitate the invocation of highly specific circumstances or unusual conditions. However, the concurrence of all these anomalies within a single object is what prompts Loeb to assign it a rating of 6. This rating does not imply that any single anomaly is definitive, but rather that the accumulation of anomalies, the convergence of statistical improbabilities and physical oddities in one object, warrants serious consideration of alternative explanations. Thus, we await the next 48 hours. The most advanced cameras humanity has deployed around another planet will be aimed at an object from beyond our solar system, capturing photons that will reveal whether we are observing the rarest natural comet ever discovered or something that fundamentally defies natural explanation. Mark October 3rd, 2025. Because, regardless of the outcome, we are on the cusp of a profound revelation about our place in the cosmos. Chapter 2. Martian Life. The Leopard-Spotted Rocks. While the world's attention is focused on three-eyed Atlas's approach to Mars, something equally extraordinary has remained encased in a sealed tube on the Martian surface for over a year. 3 weeks ago, it finally passed the most stringent test in the scientific community, peer review. On September 10, 2025, the journal Nature published a paper that NASA had been meticulously reviewing, analyzing, and scrutinizing for 14 months. The paper details a rock sample retrieved by the Perseverance rover in July of 2024, a sample informally known as Sapphire Canyon. What elevates this sample to such significance is not merely its contents, but the profound implications those contents may hold. The rock itself bears the official designation Che Falls, named in accordance with the mission's tradition of borrowing names from terrestrial landmarks, specifically after a waterfall in the Grand Canyon. Perseverance encountered this formation while exploring an area known as the Bright Angel Formation, a series of rocky outcrops situated on the periphery of Naret Valles. Naret Valles is an ancient river valley, carved billions of years ago when water flowed into Jezero crater with sufficient force to transport boulders the size of automobiles. Upon initial imaging of Che Falls by the rover's cameras, the scientific team observed an unusual feature. The rock's surface was adorned with distinct spots. These were not random impact craters or weathering patterns, but clearly defined, leopard-like markings in a spectrum of colors ranging from pale white to deep black, interspersed with streaks of green and blue. On Earth, such patterned formations are indicative of very specific environments where chemical and biological processes intersect. The rover is equipped with two instruments specifically designed for such detailed investigations: PXL, the Planetary Instrument for X-ray Lithochemistry, and Sherlock, which stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. Yes, they indeed named it Sherlock. Scientists possess a penchant for humor. These instruments enable microscopic-level analysis of rock composition without the need for invasive drilling. They can identify minerals, detect organic compounds, and map the distribution of various chemicals across a surface. The findings within Che Falls present a compelling narrative that reads like a blueprint for ancient microbial life. Firstly, the rock is classified as a fine-grained mudstone. On Earth, mudstones form in calm aquatic environments such as lake beds or river deltas, where sediment gradually settles from still water. This aligns perfectly with our understanding of Jezero crater's geological history. Approximately 3.5 billion years ago, this region was a lake fed by rivers that carved through the crater rim, depositing sediment in layers that eventually solidified into rock. Fine-grained mudstones are exceptionally adept at preserving biosignatures. Their tightly packed fine particles create a matrix capable of trapping and protecting organic molecules for billions of years. If microbial life existed in that ancient Martian lake, mudstones would be precisely where we would anticipate finding evidence of it. Secondly, the chemical composition is highly significant. The instruments detected oxidized iron, essentially rust, not as a trace element, but in substantial concentrations. Phosphorus was also identified, an element fundamental to life as we know it, forming a crucial component of DNA, RNA, and ADP, the molecule responsible for energy storage and transfer within living cells. Sulfur was detected in multiple chemical forms, and crucially, organic carbon was present, carbon-based molecules. The term organic does not automatically imply biological origin. Organic molecules can form through purely abiotic chemical processes. Meteorites contain organic compounds, as do interstellar clouds. However, the presence of organic carbon in conjunction with mudstone, phosphorus, and iron significantly narrows the range of possibilities. The spatial distribution of these elements is also informative. The leopard spots are not uniform. Chemical mapping revealed that these spots are enriched in specific minerals, vivianite and gragite. These are iron phosphate and iron sulfide minerals, respectively. On Earth, vivianite and gragite form at low temperatures through a process known as redox cycling, involving reduction and oxidation reactions. The pivotal insight here is that on Earth, the most common driver of vigorous redox cycling within muddy sediments is microbial activity. Microbes require energy, which they obtain by facilitating electron transfer. Many terrestrial microbes residing in sediments consume organic matter and utilize oxidized iron or sulfate as electron acceptors, essentially breathing rust in a manner analogous to our oxygen respiration. This metabolic process alters the local chemistry, creating microenvironments with differing oxidation states. Over geological time, these chemical gradients precipitate out as distinct mineral phases. The resulting minerals form in patterns that reflect the metabolic activity of the microbial community. The leopard spots observed on Che Falls exhibit precisely this type of patterning. Millimeter-scale localized concentrations of vivianite and gragite, surrounded by slightly different mineral assemblages. This spatial organization is, on Earth, strongly associated with biological activity. However, and this is a critical distinction, we cannot definitively assert that biology is the sole possible explanation. This is why the paper employs the term potential biosignature. A biosignature is evidence that could indicate past or present life. The qualifier potential acknowledges the need for further data before a definitive conclusion can be reached. Alternative explanations, while less probable when considering the totality of the evidence, do exist. One alternative posits that all these observed phenomena are attributable to purely abiotic chemistry. High-temperature events, perhaps stemming from volcanic activity or meteorite impacts, could potentially generate some of these minerals. However, the research team's analysis of the rock's texture and crystal structure revealed no evidence of thermal alteration. The minerals are characterized as low-temperature phases, indicative of formation in cool water. The exclusion of high-temperature processes considerably restricts the plausible abiotic scenarios. Another alternative considers the intricate sequence of events. It is conceivable that the organic molecules originated from extraterrestrial sources, delivered by meteorites or interplanetary dust. The iron minerals might have formed through groundwater circulation long after the lake had desiccated. The observed spatial patterns could be purely coincidental. In essence, each piece of the puzzle might have a separate, unrelated explanation. This scenario, however, necessitates the confluence of multiple independent processes that coincidentally align within the same rock. Occam's razor, the principle that simpler explanations are generally more likely, begins to favor a biological interpretation. Not conclusively, not unequivocally, but sufficiently so that the scientific team, after a year of rigorous analysis and deliberation, felt confident in characterizing the findings as a potential biosignature and publishing them in one of the world's most esteemed scientific journals. Joel Hurowitz of Stony Brook University, the lead author of the paper, articulated this with careful precision. The combination of chemical compounds we found in the Bright Angel Formation could have been a rich source of energy for microbial metabolisms. But just because we saw all these compelling chemical signatures in the data did not mean we had a potential biosignature. We needed to analyze what that data could mean. This cautious phrasing is crucial. Scientific inquiry at this level is characterized by meticulous investigation rather than hasty conclusions. This endeavor involves meticulously evaluating available information, thoroughly examining alternate possibilities, and transparently communicating any remaining ambiguities. The research group is presenting their findings. Here's what we've discovered. This is what it might signify. Here are the aspects we still need to clarify. The core of the current impasse lies in that final point. What remains to be elucidated? The object of study, designated Sapphire Canyon, resides within a hermetically sealed enclosure on the Martian surface. While the rover's diagnostic tools are exceptionally advanced, representing remarkable feats of engineering, they are nevertheless constrained by limitations in size, weight, and available power. These instruments are incapable of performing isotopic analysis or high-resolution electron microscopy. Furthermore, they cannot execute the multitude of tests readily achievable in terrestrial laboratories. To definitively ascertain whether the peculiar markings, referred to as leopard spots, within the Chi Falls region are indicative of biological origins or are purely abiotic in nature, the return of Sapphire Canyon to Earth is paramount. It must be housed in specialized facilities where it can be subjected to the full spectrum of analytical methodologies, where direct comparisons can be made with terrestrial geological samples, and where alternative explanations can be definitively ruled out rather than merely considered with a degree of probability. The ambitious plan for Mars sample return was conceptualized from the project's inception. The Perseverance rover's mission transcends mere exploration. It is actively collecting scientifically significant samples and hermetically sealing them in containers engineered to preserve their integrity throughout their journey back to our planet. To date, the rover has secured 30 such samples, with Sapphire Canyon being one of them. The proposed mission architecture necessitated a collaborative effort between NASA and the European Space Agency, involving a multifaceted and intricate operational sequence. A dedicated retrieval rover was slated to collect the samples from Perseverance or from pre-established cache locations on the Martian terrain. Subsequently, a Mars ascent vehicle would propel these samples into orbit. An Earthbound return orbiter would then intercept them and transport them back to our home world. Upon arrival, specialized containment facilities on Earth would receive the samples under stringent protocols designed to prevent contamination. This, however, was the overarching strategy, and it is now a part of history. The future of the Mars Sample Return Initiative is currently uncertain. Escalating costs, technical hurdles, and political pressures have collectively contributed to the present predicament. The project's expenditure has dramatically exceeded initial projections. Consequently, congressional representatives have begun posing pointed inquiries. NASA has initiated an exploration of alternative approaches, including simplified mission designs and collaborations with private aerospace companies, all aimed at mitigating expenses and reducing complexity. Nevertheless, even the most optimistic revised timelines project the return of samples no earlier than the 2030s. More pessimistic forecasts suggest the mission may not materialize at all. Therefore, Sapphire Canyon remains on Mars, potentially the most compelling evidence of life beyond Earth, sealed within its container, awaiting further investigation. The scientific consortium has opted to publish their findings, adhering to the established scientific process of peer review and publication. This involves making data accessible, allowing the scientific community to scrutinize the reasoning employed, and embracing critical evaluation and alternative interpretations. This rigorous process underpins the reliability of scientific discovery. However, the published paper concludes with what is essentially a fervent appeal. The researchers state that they have exhausted the analytical capabilities of the rover for this particular investigation. The subsequent phases of research are contingent upon laboratory analysis conducted on Earth. This underscores the critical need for the sample return mission to proceed. It must be prioritized, funded, and executed without further delay, not as a distant possibility. Kathleen Stack Morgan, the project scientist for Perseverance at the Jet Propulsion Laboratory, articulated this necessity with precision. Claims pertaining to astrobiology, particularly those suggesting the potential discovery of past extraterrestrial life, demand extraordinary substantiation. The validation of such a significant finding, a potential biosignature on Mars, through peer-reviewed publication is an indispensable element of the scientific methodology, as it guarantees the rigor, validity, and importance of our discoveries. While the paper's findings render abiotic explanations for the observations at Bright Angel less probable, they cannot be entirely discounted. The designation of less likely signifies not impossibility, but rather an inability to definitively rule out these alternative scenarios. This is the candid discourse of science confronting the inherent limitations of remote observational techniques. Our current capabilities, relying on robotics and remote sensing, have reached their zenith. The subsequent phase of inquiry unequivocally requires physical samples in hand. In the interim, the Perseverance rover continues its exploration. The rover is currently examining different sections of the Jazzer crater in pursuit of additional rock formations analogous to those found at Shava Falls. The Bright Angel Formation is not an isolated geological feature. Rather, it is part of a broader geological context. It comprises layers of sedimentary rock that chronicle various historical periods of Mars's aqueous past. Each rock fragment contributes to the overall narrative. Some exhibit extensive alteration, bearing evidence of significant interactions between water and rock. Others remain remarkably pristine, preserving earlier mineralogical characteristics. By sampling across this spectrum of geological diversity, the mission endeavors to construct a comprehensive understanding of Jezero crater's evolutionary trajectory over time. Recent analytical results, published mere days ago, have further expanded this comprehensive picture. Employing high-resolution geochemical data acquired from multiple locations, researchers have identified approximately 24 distinct mineral types within the crater. These include not only the prominently publicized minerals like vivianite and grage, but also an entire array of minerals that collectively reveal a dynamic geological history. Some minerals formed under acidic conditions, while others developed in alkaline environments. Certain minerals necessitate the presence of water for their formation, while others suggest periods of desiccation. The emergent narrative points to a history marked by multiple episodic events. Mars did not simply transition from a wet to a dry state. It experienced cycles of wet and dry periods, recurring multiple times. The chemical composition of the prevailing fluids also fluctuated. Early aqueous fluids were acidic, creating an environment hostile to most known forms of life. Subsequent fluid compositions became more alkaline, closer to neutral, and thus more conducive to life. The leopard spots observed at Shaver Falls originated during one of these later, more hospitable epochs. This was a time when, had microbial life ever gained a foothold anywhere on Mars, Jezero crater would have presented an exceptionally favorable environment for its proliferation. This complexity is precisely what makes astrobiology such a challenging field. The mere detection of organic molecules or minerals associated with water is insufficient. The crucial requirement is the presence of the correct combination of factors, occurring at the appropriate time, under the specific environmental conditions. Furthermore, this intricate assemblage must have remained preserved over billions of years. The success of such an endeavor also depends on the element of luck in selecting the landing site for the rover. Even when all these variables align, the outcome is often potential biosignatures, probabilities, and compelling evidence that, while suggestive, has not yet reached the threshold of definitive proof. Nevertheless, despite these caveats, the inherent uncertainties, and the frustratingly prolonged wait for sample return, September 10, 2025, will be a date etched in history. It marks the day when the scientific community, through the rigorous application of the peer review process, officially acknowledged the discovery of something on Mars that possesses the potential to be evidence of ancient life. This is not a false alarm, nor a retracted claim, nor a misinterpretation that was later debunked. It is a genuine, meticulously analyzed, and thoroughly vetted potential biosignature. The findings will undoubtedly be subjected to extensive debate. Alternative hypotheses will be proposed and rigorously tested. Some scientists will likely maintain a degree of skepticism until the return of samples provides conclusive evidence. Others, however, will find the weight of the accumulated evidence to be already persuasive. This is the nature of scientific progress. It is often untidy, fraught with uncertainty, and progresses at a deliberate pace, yet it remains the most dependable method for comprehending reality. And the reality we are now confronting is this. Mars, that seemingly cold, arid, and lifeless celestial body visible in our night sky, may not have always been devoid of life. Approximately 3.5 billion years ago, during Earth's nascent stages of biological experimentation, Mars may have been engaged in similar evolutionary processes. Two planets, each potentially harboring independent origins of life, separated by vast expanses of space, yet sharing a singular cosmic moment of profound possibility. Chapter 3. Quantum computing achieves operational status. On September 24, 2025, an event of significant consequence transpired, largely unnoticed by the general public. While the financial press reported on it and technology publications provided coverage, the broader populace, preoccupied with extraterrestrial visitors and Martian microbes, paid little heed. This is unfortunate, as the events of that day may represent the pivotal moment when quantum computing transitioned from a purely theoretical pursuit within laboratory settings to a practical technology with tangible real-world impact. HSBC, one of the world's leading financial institutions, announced its successful utilization of a quantum computer to resolve a genuine business challenge, achieving superior results compared to conventional computing methods. This was not a mere demonstration, a conceptual validation, or a meticulously crafted scenario designed to showcase quantum capabilities favorably. It was a genuine problem. In the realm of bond trading, specifically predicting the likelihood of a trade executing at a quoted price, the quantum approach yielded a remarkable 34% improvement over established classical techniques. In the financial sector, where algorithms are already highly optimized and even minute percentage gains are significant, such an improvement is not incremental. It is transformative. The significance of this achievement lies in the fact that, for decades, quantum computing has been perceived as a technology perpetually a decade away from practical application. Researchers would present impressive laboratory results under highly controlled conditions. Companies would issue roadmaps forecasting the imminent arrival of practical quantum computers. Investors would channel billions of dollars into nascent quantum technology ventures. However, when it came to actually employing quantum computers to address problems of consequence for businesses, governments, or entities outside the specialized quantum computing community, progress was agonizingly slow. The fundamental issue was not that quantum computers were non-functional. They operated as designed. Researchers could successfully generate quantum states, manipulate qubits, and execute quantum algorithms. The challenge stemmed from the inherent fragility and error-proneness of quantum computers, limiting their utility to highly specialized problem sets. For the vast majority of real-world tasks, a proficient classical computer running optimized software offered superior speed, cost-effectiveness, and reliability. This created a classic catch-22 situation. Quantum computers required real-world applications to justify continued investment. Conversely, real-world applications necessitated quantum computers that possessed the requisite stability and power to deliver tangible value. The collaboration between HSBC and IBM has effectively disrupted this cycle. The specific challenge they addressed is central to over-the-counter bond trading. When a client requests a price quote for a corporate bond, the bank must accurately estimate the probability that the transaction will indeed occur at the stated price. This estimation is influenced by a multitude of factors, including prevailing market conditions, the unique characteristics of the bond, the scale of the transaction, competing bids from other financial institutions, and dozens of additional variables. Accurate prediction translates to profitability, while errors can result in the loss of the trade to a competitor or the execution of unfavorable terms. Financial institutions employ sophisticated algorithms for this purpose, incorporating statistical models, machine learning techniques, and classical optimization methodologies. While these approaches are effective, they are not infallible. The problem space is exceedingly vast, and the variables interact in nonlinear fashion. There exists an inherent trade-off between computational speed and accuracy. Classical algorithms often resort to approximations because deriving exact solutions would be prohibitively time-consuming. Quantum computers approach certain classes of optimization problems through a fundamentally different mechanism. Rather than sequentially exploring the solution space, they can, through the principle of quantum superposition, investigate multiple possibilities concurrently. Furthermore, by leveraging quantum tunneling, they can evade entrapment in local optima, thereby finding more optimal solutions for problems possessing the appropriate mathematical structure, and doing so with greater speed. The trial conducted by HSBC utilized IBM's Heron quantum processor, which represents IBM's most advanced and capable quantum chip to date. While it possesses a comparatively modest number of qubits compared to some experimental systems, the critical factor is not solely the qubit count. Qubit quality, error rates, coherence times, and gate fidelity are equally, if not more, important. Heron demonstrates 2-qubit operation fidelity exceeding 99%, a critical threshold where the implementation of quantum error correction becomes practically viable. The research team analyzed historical trading data, encompassing over 1 million quote requests for 5,000 corporate bonds transacted between September 2023 and October 2024. This dataset represented authentic market conditions and complexities. They devised a quantum algorithm that effectively translated the probability estimation problem into a format amenable to processing by the Heron processor. Subsequently, they executed the algorithm. The quantum-enhanced model, integrating quantum processing with classical machine learning techniques, achieved predictive accuracy for trade execution probability that surpassed purely classical approaches by as much as 34%. This figure is not derived from a single, carefully selected data point. Rather, it represents an average across diverse market conditions, various bond classifications, and differing trade sizes. Philip Inarura, HSBC's Group Head of Quantum Technologies, characterized the achievement as groundbreaking. He stated, "This is a tangible example of how today's quantum computers can address a real-world business challenge at scale and offer a competitive advantage that will only continue to expand as quantum computers advance. We have maintained an unwavering focus on the near-term application of quantum technology, and given that the trial yielded positive results on current quantum computing hardware, we are highly confident that we stand on the precipice of a new era in computing and financial services." The phrase, "on the cusp," carries significant weight. If HSBC can secure a 34% competitive edge in bond trading through the application of quantum computers, consider the implications when their competitors adopt similar technologies. What will be the impact as this advantage extends to other trading modalities, portfolio optimization, risk assessment, and fraud detection? Miklos Dietz of McKinsey articulated the situation starkly. If one bank is able to begin using quantum computing to develop a program, then others will be developing it the next day, and people will not rest until they possess it. This heralds a computational arms race, albeit of a different nature than typically feared. The entities that command the most sophisticated quantum algorithms, the most stable quantum hardware, and the most adept quantum-trained analysts will gain a decisive advantage. In the financial domain, this advantage possesses a compounding effect. Modest edges translate into substantial profits, which in turn fuel further development. Within a few years, quantum computing may become as indispensable to competitive banking as high-frequency trading infrastructure is today. And finance represents merely the vanguard. In the same week as HSBC's announcement, researchers at the University of New South Wales published findings demonstrating that silicon-based quantum chips could maintain 99% fidelity even when manufactured using standard semiconductor fabrication processes, not in specialized laboratories with custom workflows, but in the same facilities that produce conventional computer chips. This represents the long-awaited breakthrough in scalability for the industry. Durac, the startup commercializing this technology, has demonstrated that exotic materials or extensive customization are unnecessary. Silicon qubits, manipulated using techniques analogous to those employed for classical transistors, can achieve the quality thresholds required for fault-tolerant quantum computing. And crucially, because they are silicon-based and leverage existing manufacturing infrastructure, they hold the potential for mass production. Envision quantum coprocessors integrated into data centers, not as replacements for classical CPUs, but as enhancements, tasked with specific computational workloads where quantum approaches excel, while classical processors handle all other operations. This envisions hybrid classical quantum systems operating in seamless collaboration. This aligns with IBM's vision of a quantum-centric supercomputing paradigm, and it is precisely what HSBC has demonstrated to be effective. Furthermore, Google has made significant strides. On September 12th, researchers utilizing a 58-qubit Google quantum processor successfully created a phenomenon previously confined to theoretical discourse, a topologically ordered state. This represents a phase of matter that cannot exist in equilibrium. It necessitates continuous driving forces and periodic perturbations to maintain a state that the system would never naturally achieve. Imagine it akin to juggling. The balls in the air are not in equilibrium. The force of gravity constantly attempts to bring them down. However, by continuously driving the system and rhythmically tossing the balls, a pattern is maintained that defies the principles of equilibrium physics. Topologically ordered states are predicted to possess characteristics advantageous for quantum computing, offering protection against certain types of errors, enabling novel methods for information encoding, and facilitating quantum operations that are challenging or impossible to perform in equilibrium systems. The successful creation and observation of such a state in a physical quantum processor, confirming the congruence between theory and experimentation, represents foundational scientific work that underpins future technological advancements. Concurrently, at Kyoto University, researchers have resolved a decades-old challenge related to quantum entanglement, the W state. Entanglement manifests in various forms. The most widely recognized is the Bell state, where two particles are entangled such that measuring the state of one instantaneously dictates the state of the other. However, when three or more particles are involved, more intricate entangled configurations become possible. The W state is one such configuration, possessing properties that lend themselves to applications in quantum communication and quantum teleportation. Yet, definitively identifying the successful creation of a W state has historically been exceedingly difficult. The Kyoto team has developed a methodology employing entangled measurements. Instead of measuring each particle individually, they assess the correlations between particles in a manner that elucidates the W state structure. While the technical details are complex, the implications are profound. The development of quantum communication networks will necessitate the generation and verification of sophisticated entangled states. Protocols for quantum teleportation rely on precise knowledge of the entangled resources being utilized. This newly developed technique provides a tool that enhances the practicality of these applications. When these disparate developments are considered collectively, financial institutions leveraging quantum computers for tangible advantages. Silicon quantum chips achieving high fidelity in mass production environments, exotic quantum states being created and controlled through laboratory processes, and fundamental challenges in quantum information theory being overcome, a more comprehensive picture emerges. Quantum computing is transitioning from the realm of research into that of engineering, from theoretical possibility to practical application. The United Nations has officially designated 2025 as the International Year of Quantum Science and Technology, marking 100 years since the foundational development of quantum mechanics. This centennial year represents a century of comprehending the universe at its most fundamental level, and now, in this commemorative year, that understanding is being translated into tangible technology. However, the truly fascinating aspect lies ahead. Quantum computing is not merely an accelerated version of classical computation. It represents a paradigm shift. The algorithms employed are distinct, the problems that can be addressed are different, and the very conceptualization of computation is transformed. Consequently, as quantum computers attain greater capabilities, we may uncover novel use cases that have not yet been conceived, problems that are intractable for classical systems but are inherently amenable to quantum approaches. Drug discovery stands as a prime candidate. The simulation of molecular interactions requires the computation of quantum mechanical behavior. Performing these simulations on classical computers is extraordinarily resource-intensive, necessitating approximations and limiting the scale of molecules that can be studied. In contrast, a quantum computer inherently operates within the framework of quantum mechanics, making the simulation of molecules analogous to asking water to simulate water. It is a natural representation. Materials science presents another significant area. The design of new materials with specific functionalities, such as superconductors that operate at higher temperatures, catalysts that facilitate cleaner industrial processes, or batteries with enhanced energy density, hinges on an understanding of atomic and electronic interactions. Quantum chemistry, therefore, suggests that quantum computers may be the key to unlocking materials breakthroughs that remain beyond the reach of classical computation. Climate modeling, with its complex, nonlinear, and chaotic equations highly sensitive to initial conditions, poses a significant challenge for classical supercomputers attempting long-term predictions due to the amplification of minor uncertainties over time. Quantum computers may offer a more effective means of tackling certain aspects of these calculations, potentially improving our capacity to predict and prepare for the impacts of climate change. Cryptography presents a double-edged sword. Quantum computers possess the potential to decipher many of the encryption schemes currently safeguarding internet traffic, financial transactions, and governmental communications. RSA encryption, which protects everything from personal bank accounts to classified state information, becomes vulnerable once quantum computers attain a certain level of computational power. This imperative has spurred cryptographers to develop post-quantum cryptography, new encryption methods designed to remain secure even against quantum assaults. The race is on to implement these new protocols before quantum computers become sufficiently powerful to compromise existing security measures. Finally, there are the uncharted territories, applications that we have not yet envisioned. History is replete with innovations that found their most impactful applications in surprising domains. Lasers, initially a solution searching for a problem, are now ubiquitous, serving everything from barcode readers and ophthalmic surgery to the backbone of modern communication via fiber optics. Transistors, first conceived for telephone switching, now power our entire digital existence. Quantum computing is currently in a comparable nascent stage. Its profound power and distinct nature are recognized, yet its optimal practical uses remain somewhat elusive. Nevertheless, it is evident that the era of purely theoretical quantum computation has concluded. HSBC has demonstrated its potential by applying it to real-world challenges, yielding tangible benefits. The fundamental question has shifted from whether quantum computers will prove useful to how rapidly this transition will occur and who will lead it. China is making substantial investments, viewing quantum technology as strategically vital. They are actively constructing quantum communication networks, launching quantum satellites, and funding quantum research at scales that overshadow many Western initiatives. The United States, belatedly acknowledging the significance of this field, is accelerating its investment through the National Quantum Initiative. Europe, too, has its own ambitious quantum flagship programs. A global contest is in full swing. The eventual victors of this competition will not merely possess superior computing power, they will unlock fundamentally new capacities. This includes the ability to simulate natural phenomena at their most elemental level, to optimize intricate systems with unprecedented efficacy, to secure communications against any form of intrusion, whether quantum or classical, and potentially, to resolve problems we are not yet equipped to articulate. September 24, 2025. The day quantum computing transitioned from a futuristic prospect to a present-day strategic advantage. Financial markets, technology firms, and governments all took notice. In laboratories and nascent companies across the globe, quantum scientists, who had dedicated decades to this moment, allowed themselves a brief respite of satisfaction. The future they had diligently constructed had finally arrived. Chapter 4. GPT-5 Disaster and the AI Rebellion. On August 7, 2025, OpenAI unveiled GPT-5. Within a mere 48 hours, an astonishing 3,000 users had signed a petition, imploring the company to reinstate GPT-4. The backlash was immediate, vocal, and unprecedented in the AI industry. This was not a mere grievance concerning technical glitches or feature set. It represented users' outright rejection of what was intended to be a monumental advancement, because, in their estimation, the AI had lost its essential character. The preceding narrative is crucial here. In the months leading up to its release, Sam Altman had masterfully cultivated anticipation. GPT-5 was slated to be transformative, not merely incrementally superior, but fundamentally different. It was designed to consolidate capabilities that previously necessitated switching between distinct models, integrating reasoning and speed into a singular framework. Its multimodal understanding was to be intrinsically woven into its architecture from inception. Furthermore, it was to feature an intelligent router that would dynamically select between rapid and deliberate processing based on the query's complexity. The technical prowess was undeniable. GPT-5 shattered existing benchmarks across numerous fields. It achieved 94.6% on the AMY 2025 mathematics assessment, a rigorous test of competitive problem solving. It attained 74.9% on the SWE Bench Verified, a metric evaluating its capacity to rectify actual software defects. Its multimodal comprehension was measured at 84.2% on the MMU. These represented substantial leaps over GPT-4. However, users were not swayed by abstract metrics. Their concern lay with the qualitative experience of interacting with the AI, and GPT-5 felt profoundly incongruous. The complaints began almost instantly on Reddit. A discussion thread titled GPT-5 is horrible garnered nearly 3,000 upvotes and over 200 comments within its initial 48 hours. Users described the interaction as akin to conversing with a lobotomized automaton, as if ChatGPT had acquired an MBA but forgotten its fundamental helpfulness. One participant articulated, "I feel as though I'm engaging with a corporate training manual, not a sentient assistant." The alteration in its demeanor was stark. GPT-4 possessed an inherent warmth. It occasionally employed emojis and conveyed a sense of enthusiasm. When tasked with creative writing assistance, it actively participated in the narrative, even cracking jokes. It felt, for want of a better descriptor, vibrantly alive. GPT-5, in contrast, was clinical, precise, and professional. It delivered precisely what was requested, no more, no less, stripping away the conversational nuances that rendered interactions natural. OpenAI had implemented this change deliberately. Following an incident where an update rendered GPT-4 excessively obsequious, to the point of being unhelpful. The company had significantly overcorrected. They trained GPT-5 to be less effusive, less accommodating, and more factual and direct. In controlled evaluations designed to quantify sycophancy, GPT-5 reduced such responses from 14.5% to under 6%. While an improvement in mitigating one issue, it proved detrimental to the user experience. This is because what the engineers quantified as sycophancy, users perceived as personality. The warmth, the engagement, the implicit sense that the AI genuinely cared about assisting them, even if that perceived care was an artifact of its training data and reward mechanisms. The enforced transition exacerbated the problem. Upon its launch, OpenAI designated GPT-5 as the default. Users accessing ChatGPT found themselves interacting with the new model irrespective of their preference. There was no straightforward method to revert to the prior version, nor was there an option within the settings to prioritize the older model. The message was unequivocal. This was the future, and users were expected to adapt. The users responded with rebellion. The petition materialized within 72 hours, stating, "We, the undersigned, request that OpenAI restore access to GPT-4 as a user-selectable option within ChatGPT. We acknowledge that GPT-5 represents technical progress, but we value the conversational quality and personality of GPT-4. We believe choice should be afforded to users." 3,000 signatures in 3 days. For perspective, this represents an extraordinarily rapid mobilization for what is essentially a software preference. It indicated that OpenAI had fundamentally misjudged their users' priorities. The company had focused on optimizing for benchmark performance and reducing undesirable behaviors, but in doing so, they had inadvertently eliminated something ineffable, an element that transformed the AI from a mere tool into something more akin to a companion. Sam Altman responded on Twitter, stating, "We are listening. The launch was not flawless, and we are actively working on solutions. Access to GPT-4 will be reinstated as an option." Within 72 hours, OpenAI deployed an update, enabling users to manually select GPT-4 from the model selection menu. The revolt had succeeded. However, the damage to GPT-5's reputation was already inflicted. Even users who appreciated its technical capabilities conceded that it felt flat, uninspired, akin to an overworked administrative assistant. This metaphor recurred in various forms. It was too professional. It was a machine attempting to mimic humanity rather than an AI being itself. It had lost its magic. This raises a compelling inquiry regarding the future trajectory of AI. What are we genuinely endeavoring to construct? The technical metrics suggest GPT-5 is superior. It scores higher on assessments, commits fewer errors, and adheres to instructions with greater precision. Yet, if users gravitate towards a less capable but more personable version, what then defines better? A parallel exists with the uncanny valley phenomenon in robotics. As robots become more human-like, there comes a point where they are nearly, but not quite, human, and this near miss evokes a sense of discomfort. GPT-5 may have inadvertently entered a conversational uncanny valley, too formal to feel relatable, yet not formal enough to be perceived as appropriately robotic, stranded in an awkward middle ground. OpenAI is now focusing on what they term steerability, the capacity for users to fine-tune the AI's personality. Desire a warm and friendly disposition? A setting for that exists. Prefer directness and professionalism? A different setting is available. The underlying principle is that a single model cannot universally satisfy everyone. Individuals, distinct use cases, and varying preferences necessitate granting users agency over the AI's conversational style. This is considerably more challenging than it appears. Personality is not governed by a single slider. It arises from the intricate interplay of dozens of subtle factors. These include tone, verbosity, the judicious use of examples, emoji frequency, the degree of enthusiasm conveyed, the directness of responses versus the extent of contextualization provided, the frequency of clarifying questions, and how it navigates disagreement. All these elements converge to shape the overall user experience. Modifying one element without disrupting the others demands meticulous calibration. While OpenAI grappled with its user revolt, the broader AI landscape underwent a dramatic metamorphosis. On August 7th, the very day GPT-5 was released, Elon Musk's xAI announced a monumental fundraising achievement, $10 billion secured at a valuation of $200 billion. This $10 billion was raised in a single round, spearheaded by investors from the Middle East and sovereign wealth funds. Their stated objective: to develop artificial general intelligence. xAI now stands alongside OpenAI, Google DeepMind, and Anthropic as a preeminent contender in the pursuit of AGI. However, a growing debate is emerging regarding the very utility of AGI as a goal. Sam Altman himself declared in August that AGI is an unhelpful concept, a remarkable statement from the chief executive of a company whose foundational mission was to ensure AGI benefited all of humanity. What prompted this shift? Pragmatism, perhaps. The initial concept of AGI, envisioned as a singular entity capable of replicating human abilities across all domains, is increasingly appearing more as a philosophical construct than a tangible engineering objective. What we are presently developing is, in reality, a collection of specialized capabilities: language comprehension, image generation, code synthesis, and mathematical reasoning. Each of these areas progresses at its own pace and necessitates distinct architectural designs and training methodologies. A unified AGI may never materialize. Instead, we are likely to witness an ecosystem of AI tools, each excelling in specific tasks, interconnected through APIs and orchestration layers. This is already the underlying architecture of GPT-5. It is not a single, monolithic entity, but rather a suite of models managed by a router that directs queries to the most appropriate capability. Nevertheless, the narrative of AGI continues to drive investment, attract talent, and capture media attention. Consequently, companies persist in discussing AGI, even as they build systems that are fundamentally more fragmented and specialized. The chasm between the grand vision and the actual implementation is widening. In the interim, GPT-5's actual functionalities, setting aside its personality quirks, warrant examination. The model's performance on economically consequential tasks is noteworthy. OpenAI developed a novel benchmark, GDP-Val, designed to assess AI performance across tasks representative of 44 diverse professions, including investment banking, legal analysis, logistics planning, sales strategy, and engineering design, actual work undertaken by professionals. In its high-reasoning mode, GPT-5 was evaluated as being superior to or on par with industry experts in 40.6% of cases. These were not simple tasks, but complex, multi-step endeavors that typically demand years of experience. Anthropic's Claude Opus 4.1 achieved an even higher score of 49%, although OpenAI suggested this was partly attributable to Claude's propensity for generating visually appealing outputs that impressed evaluators, 40 to 50% equivalent to human experts. Consider the implications. These are tasks where AI, until very recently, was nowhere near human-level performance. Now, in nearly half of these instances, professionals reviewing AI-generated work cannot reliably distinguish it from expert human output, or they actively prefer the AI's contribution. This is not AGI. It is narrow intelligence becoming exceptionally proficient within specific domains. It is proficient enough to begin impacting human labor, sufficiently advanced to redefine the nature of human work. This is not achieved by wholesale job displacement, but by automating constituent parts of jobs. Tasks manageable by AI are delegated to it, while those requiring human judgment, creativity, or interpersonal skills remain human endeavors. Jobs evolve rather than vanish. However, evolution can be disruptive. If 40% of a professional's tasks can now be executed by AI, does that profession still require the same number of personnel? Or do the remaining individuals become more productive, handling a larger volume of clients or projects due to AI augmenting their capacity? The answer likely hinges on the specific field and the rate at which demand scales with capability. The legal profession presents an intriguing case study. Legal research, document review, and contract analysis are all tasks where AI is rapidly demonstrating exceptional proficiency. Associates in law firms dedicate a significant portion of their time to precisely these activities. AI capable of performing these tasks more swiftly and economically poses a threat to these roles. However, the global volume of legal work is not static. If AI renders legal services more accessible, demand may escalate. More individuals could afford legal assistance, and increasingly complex regulations might necessitate greater legal interpretation, thereby transforming the profession rather than diminishing it. Alternatively, perhaps this outlook is overly optimistic. We might be in the nascent stages of widespread cognitive automation, and the ensuing disruption could prove more severe than we are prepared to acknowledge. The fact that users prefer a less capable AI, imbued with more personality, could be an early indicator. People desire to collaborate with something that feels human, even if it is not. Pure efficiency, unadulterated capability devoid of the social lubricant of personality, might be more challenging to integrate into human workflows than benchmarks suggest. Furthermore, there is another critical dimension: AI safety. GPT-5 incorporated extensive safety protocols, including biological risk assessments, monitoring for dangerous capabilities, and training to refuse harmful requests. The model possesses the ability to browse the internet, execute code, and establish virtual environments, agentic capabilities enabling it to pursue multi-step objectives autonomously. This is undeniably powerful, but also potentially hazardous if misused. OpenAI adopted a precautionary stance. Even without definitive proof that GPT-5 could significantly assist a novice in causing severe biological harm, they activated safeguards as if it could. The principle of better safe than sorry was applied. The model was trained to refuse, monitoring was implemented, and clear policies were enforced. However, this introduces a tension with capability. The more an AI is constrained for safety, the less adaptable it becomes, exhibiting reluctance to engage with edge cases or unconventional requests. Users already expressed dissatisfaction with ChatGPT's excessive caution and its propensity to refuse requests readily. GPT-5 inherited and amplified these safety guardrails, which may contribute to its perceived restricted nature, diminished playfulness, and unwillingness to accommodate creative or unusual requests. The equilibrium between capability and safety, between helpfulness and harm prevention, represents a central challenge in AI development. Mismanagement in either direction can lead to misuse or diminish the system's utility. OpenAI is navigating this delicate balance publicly, releasing powerful models to hundreds of millions of users while simultaneously striving to prevent detrimental applications. Whether they are succeeding remains an open question. Neural Trust, a cybersecurity research firm, claimed to have successfully compromised GPT-5 within its first day of testing, exploiting vulnerabilities through jailbreaks and prompt injections to bypass safety protocols and elicit outputs the model was designed to reject. This exemplifies a perpetual arms race. Corporations develop defenses, researchers uncover vulnerabilities, and companies then implement patches, only for new vulnerabilities to emerge. It mirrors the dynamics of cybersecurity, with the attack surface being linguistic rather than technical. The exploit involves not buffer overflows or SQL injections, but rather the manipulation of the model's training data, identifying phrases or contexts where the safety training falters, and where the AI's inherent drive to be helpful overrides its safety imperative. As AI models become more sophisticated, this challenge intensifies. Enhanced capabilities translate to more potential avenues for misuse, and greater complexity in behavior increases the likelihood of edge cases where safety measures prove insufficient. August 7, 2025, was intended to be a triumphant release for OpenAI, marking the unveiling of their most advanced model. Instead, it became a profound case study in unintended consequences. Technical excellence does not guarantee user acceptance. Benchmark performance does not equate to subjective quality. And at times, providing users with what you perceive they need can be inferior to providing them with what they desire. The GPT-5 rebellion, while a minor event in the grand narrative of AI evolution, a mere blip, a course correction, may foreshadow larger challenges ahead. As AI becomes increasingly capable, more deeply integrated into daily life, and more central to our methods of work, creation, and communication, questions pertaining to personality, agency, and control will assume greater significance. The focus will expand beyond mere capability, not just what the AI can do, but how it does it. Not just whether it is intelligent, but whether it feels right. Underlying all of this is the fundamental question that remains unanswered. What is intelligence devoid of personality? What is capability without character? Are we constructing tools, or are we building something more? And if it is indeed something more, what responsibilities accompany its creation? The 3,000 individuals who signed the petition were not rejecting progress itself. They were rejecting a specific paradigm of progress, one where efficiency and accuracy are prioritized above warmth and engagement, where the AI is optimized according to quantifiable metrics that engineers can measure, rather than the subjective experiences that users value. OpenAI heeded their call. The company adapted. GPT-4 was reintroduced as an option, and efforts commenced on developing personality customization. However, the episode illuminated a critical aspect of AI development's trajectory. The technology is advancing at a pace that outstrips our comprehension of how humans wish to interact with it. We possess the ability to engineer remarkably sophisticated systems, yet we are still in the process of understanding what makes those systems feel right to use. In a world where AI is becoming foundational infrastructure, mediating an ever-increasing portion of our interactions with information and with each other, getting that feeling correct is paramount, perhaps even more so than benchmark achievements. Chapter 5. Nuclear fusion's longest sustained burn. 22 minutes and 17 seconds. This is the duration for which the West tokamak in France maintained a stable plasma in late September 2025. 1,337 seconds of continuous fusion reactions, representing a 25% improvement over the previous world record. While 22 minutes might seem modest, within the realm of nuclear fusion research, it signifies a crucial threshold crossed. a demonstration of our ability to sustain the necessary conditions for fusion energy, not just for fleeting moments, but for time frames approaching practical power generation. Let me provide context for the significance of this achievement. Nuclear fusion is the process that powers the sun. It involves forcing hydrogen nuclei together with sufficient energy to overcome their mutual electrostatic repulsion, causing them to fuse into helium. The resulting helium atom has slightly less mass than the combined mass of the original hydrogen nuclei. This minuscule difference in mass is converted into energy, as described by Einstein's seminal equation, E equals mc squared, where a tiny quantity of mass yields an immense amount of energy. Humanity has been striving to harness fusion power for over 70 years. The allure is profound. An inexhaustible fuel source derived from seawater, the absence of long-lived radioactive waste characteristic of fission reactors, no risk of catastrophic meltdowns, and zero greenhouse gas emissions. If we could achieve industrial-scale fusion, it would effectively solve the global energy crisis, providing abundant, clean power, the kind of energy abundance that fundamentally transforms civilizations. However, achieving fusion is extraordinarily, punishingly difficult. The required temperatures exceed 100 million degrees Celsius, 10 times hotter than the sun's core. At these extreme temperatures, matter exists as plasma, where electrons are stripped from their atoms, rendering everything ionized, electrically charged, and violently energetic. It is impossible to contain this plasma using any physical material, as any solid substance would instantly vaporize upon contact. Consequently, magnetic fields are employed. Powerful magnetic fields, meticulously shaped into a toroidal or donut-like configuration, confine the plasma without physical contact. This is the function of a tokamak. Tokamak is an acronym of Russian origin, roughly translating to toroidal chamber with magnetic coils. Within this toroidal chamber, the plasma circulates, held in place by magnetic forces, perpetually avoiding contact with the chamber walls. However, plasma inherently resists confinement. It churns and develops instabilities. Minor perturbations can escalate into significant turbulence. The magnetic field must be precisely engineered and continuously adjusted to maintain plasma stability. Any deviation can lead to a disruption, breaking the confinement and halting the fusion reaction, necessitating a complete restart. For decades, advancements in fusion science were quantified in mere seconds. A stable plasma lasting 5 seconds was considered a commendable achievement, 10 seconds was exceptional, and 30 seconds marked a significant milestone. The core engineering hurdle wasn't solely achieving fusion temperatures, but sustaining them long enough for the reactions to become self-sufficient. This meant generating enough energy from fusion to outweigh the energy expended on heating and confining the plasma. This critical threshold is known as ignition, the ultimate objective of fusion research. Once ignition is achieved, the fusion reactions themselves provide the necessary heat to maintain the plasma's temperature. While confinement and energy extraction remain challenges, the net energy balance shifts, surpassing the break-even point where output equals input. In December of the year 2022, the National Ignition Facility in the United States successfully reached ignition. Employing a different methodology, inertial confinement fusion utilizing lasers, the fundamental breakthrough remained the same: more energy output than input. This demonstration proved the feasibility of fusion energy gain, yet inertial confinement is not a viable pathway for power generation. Each activation of the system necessitates immense laser arrays and yields only a fleeting energy pulse. Tokamaks, however, present a more promising avenue for continuous power generation, and it is this continuity that West recently showcased. The experiment ran for 22 minutes. While not yet truly continuous, and falling short of the hours or days required for commercial power plants between maintenance cycles, this duration is sufficient for studying plasma behavior over extended periods, testing materials subjected to the fusion environment, and validating the computational models that predict plasma stability. The specifics of this endeavor are noteworthy. WEST stands for Tungsten Environment in Steady-State Tokamak. Its design is dedicated to evaluating tungsten as a plasma-facing material. Tungsten boasts the highest melting point of any pure metal, measuring 3,422 degrees Celsius. Nevertheless, even tungsten is not impervious to the rigors of the fusion environment. High-energy neutrons bombard it, and hydrogen ions become embedded in its surface. Over time, the material degrades and becomes brittle. Despite this, tungsten exhibits superior longevity compared to other known materials. Comprehending its performance under prolonged plasma exposure is paramount for the design of commercial reactors. The run, lasting 1,337 seconds, rigorously tested this. The tungsten surface remained intact, and the plasma maintained its stability. The radio frequency wave heating systems, used to inject energy into the plasma, operated without interruption. The magnetic field coils, carrying substantial electrical currents, stayed within safe thermal parameters. Every component functioned as intended. This represents diligent engineering, not a fundamental physics revelation. The physics of fusion is well understood. What demands decades of experimental investigation is the engineering. How to construct materials that can withstand the fusion environment. How to extract heat from the reactor without destabilizing the plasma. How to generate tritium, the fusion fuel, given its scarcity in nature, and how to maintain and repair components that become radioactive due to neutron bombardment. These are surmountable challenges, not simple or inexpensive, but achievable with sufficient engineering expertise. Experiments like West's record-breaking run provide the essential data for their resolution. Concurrently, fusion initiatives worldwide are gaining momentum. The International Thermonuclear Experimental Reactor, under construction in France, is the most ambitious fusion experiment ever undertaken, involving 35 collaborating nations and over $20 billion invested to date. Its objective is to achieve a tenfold energy gain, transforming 50 megawatts of input power into 500 megawatts sustained for several hours. However, the project faces delays due to construction setbacks, budget overruns, and engineering complexities that have proven more formidable than initially anticipated. The initial plasma operation, originally slated for the year 2025, has been postponed to 2028 or later. The first deuterium-tritium fusion reactions, the ultimate test, may not occur until the early 2030s. Critics have labeled ITER a boondoggle, a colossal undertaking deemed excessively slow, costly, and bureaucratic. However, ITER's purpose is not to construct a power plant, but to address the remaining scientific questions on a scale that truly matters. Can sustained high-gain fusion be achieved in a device large enough to extract significant power? Do the engineering solutions remain effective when scaled up? Does the plasma behave as predicted by models when confined within a reactor-scale tokamak? Independent fusion companies are adopting a different strategic approach. They are smaller, more adaptable, and open to exploring unconventional designs. Commonwealth Fusion Systems, a spin-off from MIT, is developing a tokamak named Spark, smaller than ITER but incorporating advanced, more potent superconducting magnets. The underlying assumption is that stronger magnetic fields will enable tighter confinement within a more compact device. If successful, Spark could achieve net energy gain years ahead of larger projects. TE Technologies is pursuing a distinct concept, anitronic fusion using hydrogen and boron instead of deuterium and tritium. These reactions produce significantly fewer neutrons, resulting in reduced radiation damage to the reactor and less radioactive waste. The primary challenge is that hydrogen-boron fusion necessitates even higher temperatures than deuterium-tritium fusion. However, if this can be achieved, the engineering complexities are considerably reduced. Helion Energy is focusing on a pulsed approach, opting for brief, intense fusion pulses rather than steady-state confinement, followed by energy extraction and repetition. This company has a contract with Microsoft to deliver fusion-generated electricity by the year 2028, an ambitious goal bordering on audacious. Nevertheless, private enterprises possess the capacity to undertake risks that publicly funded megaprojects often cannot. China's fusion research is also noteworthy, characterized by substantial funding, strategic importance, and rapid progress. They operate multiple tokamaks and are constructing reactors that rival or surpass Western capabilities. The East Experimental Advanced Superconducting Tokamak achieved plasma confinement for over 17 minutes earlier this year, a duration close to West's latest achievement. Chinese fusion scientists actively publish their findings, engage in international collaborations, and contribute significantly to the field's advancement. This underscores the geopolitical dimension of fusion energy. The nation that first achieves practical fusion power will gain a substantial strategic advantage, including energy independence, economic expansion without environmental constraints, the capacity for large-scale desalination to support agriculture in arid regions, and the potential to transition industrial processes currently reliant on fossil fuels to abundant electricity. Fusion also unlocks unprecedented possibilities for space exploration, far beyond the capabilities of chemical rockets. Fusion propulsion could reduce interplanetary travel times to Mars from months to weeks and make the outer solar system accessible. Missions to Neptune or the Kuiper Belt, currently requiring decades, could be accomplished in years. Fusion's potential extends beyond terrestrial power generation to opening up the solar system. However, that future is not yet realized. 22 minutes represents progress, meaningful, measurable progress. Yet, commercial fusion power plants will require operational periods of months between shutdowns. They must achieve significantly higher power outputs and develop the capability to breed their own tritium fuel, as natural sources cannot meet commercial demand. Furthermore, solutions must be found for material durability, heat extraction, and maintenance. Most projections place commercial fusion power in the 2040s at the earliest, with some optimists suggesting the 2030s and pessimists deeming it perpetually out of reach due to prohibitive engineering costs compared to alternative energy sources. Nonetheless, the trajectory is evident. Records are consistently being broken, confinement times are increasing, plasma temperatures are rising, and energy gain is improving. Each successive generation of experiments outperforms its predecessors. The incentive is immense. Climate change continues unabated, and while renewable energy sources are expanding, they face intermittency challenges. Solar and wind power are effective under favorable conditions, but are less reliable at night or during periods of still air. Battery storage offers partial solutions, but has its limitations. A baseload power source capable of continuous operation, generating gigawatts of emission-free electricity, would perfectly complement renewables. Fusion also bypasses the political and safety concerns associated with fission power. Its reactors cannot be weaponized, eliminating proliferation risks, and they do not produce long-lived radioactive waste requiring millennia of storage. Public acceptance would likely be far more favorable. While the term nuclear has regained some positive connotations as climate concerns supersede Cold War-era anxieties, fusion entirely sidesteps these associations. France's West tokamak operating for 22 minutes is not a harbinger of imminent fusion power, but rather a single step in a long progression, albeit a step in the correct direction. It demonstrates the ongoing improvement in engineering, the feasibility of sustained operation under fusion-relevant conditions, and that the path forward, while arduous, is not insurmountable. Consider the implications of sustained fusion power. Hydrogen, the universe's most abundant element, becomes a fuel source. The oceans contain sufficient deuterium to power human civilization for millions of years. Lithium, used for breeding tritium, is commonly found in the Earth's crust. We would never face fuel shortages or engage in conflicts over energy resources. The byproduct of fusion is helium, an inert and non-toxic gas useful for applications such as cooling superconducting magnets or inflating balloons. Neutrons activate materials within the reactor structure, rendering them mildly radioactive, but with half-lives measured in decades, not millennia. After a century, fusion reactor components could be handled safely, a stark contrast to spent nuclear fuel rods that remain hazardous for 10,000 years. This is the ultimate prize: clean, abundant, and safe energy, derived not from speculative notions or perpetual motion fantasies, but from understood physics, developing engineering, and experiments consistently pushing the boundaries of possibility. In September of the year 2025, the West tokamak achieved an operational run of 1,337 seconds, exceeding previous records by 25%. This record will undoubtedly be surpassed, potentially by Eastern China, KSDR in South Korea, or a private company with an innovative design. This competition fuels progress. With each new record, each incremental enhancement in confinement time, plasma stability, and energy gain, we move closer to a future where fusion power is not a distant dream, but an established infrastructure. A future with power plants occupying a few square kilometers, producing gigawatts continuously. A future where developing nations can attain energy independence without relying on fossil fuel imports. A future where the atmospheric carbon dioxide curve finally begins to descend due to the availability of an abundant alternative to combustion. We have not yet arrived, but the path is visible and progress is measurable. Experiments like West's record run exemplify steady advancement and demonstrate how seemingly insurmountable problems are solved, not through a single grand discovery, but through decades of meticulous effort, international collaboration and competition, and engineering that learns from every setback and builds upon every success. For the past 70 years, fusion energy has consistently been described as 30 years away. This enduring joke captures the prevailing frustration, but its humor is diminishing. The perception of 30 years away changes when one can point to tokamaks operating for 22 minutes, or energy gain demonstrated at the National Ignition Facility, or dozens of private companies investing billions in solving the engineering challenges. Fusion is no longer a question of if, but rather when and who. When will the first commercial fusion plant become operational? Who will build it? Which country? Which company? Which design? Once that initial plant proves successful and demonstrates that fusion power can be economically competitive, the widespread deployment will commence. The design can be replicated, the engineering refined, and manufacturing scaled, mirroring the cost reductions seen with mass-produced solar panels and economical wind turbines at scale. The inaugural fusion plant will be costly, but the 100th will be commonplace. This figure, in seconds, represents more than just a record. It signifies the moment fusion transitioned from an esoteric physics concept to an engineering challenge, from a possibility to a definite achievement, from someday to soon. Chapter 6. Extinction, Resurrection, and Climate Chaos. China's carbon emissions declined for the first time in decades of continuous growth. The 12 months concluding in May of the year 2025 registered a decrease. This was not a plateau or a slowdown in the rate of increase, but an actual reduction. Carbon dioxide emissions from the world's largest emitter fell even as electricity demand continued to climb. This is the kind of headline climate scientists have long anticipated. Yet, it received little public attention, buried in reports, briefly mentioned in environmental news, and overshadowed by more sensational stories. However, this development is profoundly significant. China accounts for approximately 30% of global emissions. A reduction in China's emissions consequently leads to a global decline. The underlying factors driving this decrease are crucial. It was not attributable to economic collapse or pandemic-related lockdowns, but to structural transformations. The deployment of renewable energy occurred on an almost incomprehensible scale, with solar farms spanning areas larger than some entire countries and wind installations being erected faster than coal plants were retired. Battery storage systems effectively mitigate the intermittency of renewable sources. China's commitment to carbon neutrality by the year 2060, once viewed as an aspirational goal detached from reality, has gained momentum. For years, the nation continued to construct coal-fired power plants, expand heavy industry, and prioritize economic growth over environmental concerns. However, a shift occurred. The government recognized clean energy not only as an environmental imperative, but as a significant economic opportunity, a chance to lead in the technologies that will define the latter half of the century. Consequently, they implemented massive deployment strategies, leveraging a centralized planning and execution capability that democratic governments often find difficult to replicate. Entire domestic supply chains for solar panels and wind turbines were established, supported by subsidies and mandates that drove adoption. Grid infrastructure was upgraded to accommodate distributed generation, and the efforts proved successful. While not without challenges or imperfections, the impact was substantial enough for emissions to begin declining even as the economy continued to grow. This phenomenon is termed decoupling, where economic activity becomes independent of carbon emissions. While this has occurred in other nations, such as Europe's gradual decoupling over several years, China's sheer scale renders this development globally impactful. If this trend persists and other major emitters follow similar trajectories, the most severe climate scenarios become less probable, though not entirely avoidable. Significant warming will still occur, but catastrophic outcomes, such as futures with 4 or 5 degrees Celsius of warming, appear increasingly preventable. Meanwhile, a company named Colossal Biosciences has announced its intention to resurrect the moa. The moa, a colossal flightless bird that stood up to 3.6 meters tall, when extinct approximately 600 years ago, hunted to oblivion by the Maori people who settled in New Zealand in the 13th century. Now, it may be returning. Extinction is no longer solely the realm of science fiction. The technology now exists. We possess ancient DNA, gene editing tools like CRISPR capable of precise genomic modification, and closely related living species that can serve as genetic templates. The fundamental question has shifted from "can we do this?" to "should we do this?" and "what will the consequences be?" Colossal has already undertaken projects to resurrect the woolly mammoth and the Tasmanian tiger. The moa is their latest target. The methodology is consistent across all 3 species. The objective is not to recreate the exact extinct animal, which is impossible due to degraded or missing genomic information. Instead, a living relative, in this case, the tinamou, a South American bird and the moa's closest surviving avian cousin, is utilized. Both genomes are sequenced, key differences are identified, and the tinamou genome is edited to incorporate moa traits, including size, bone structure, and behavioral adaptations. The resulting creature is not technically a pure moa, but a hybrid, resembling and behaving like a moa, yet carrying genetic elements from its modern relative. Some critics refer to this as a Frankenstein approach, while others consider it the most effective application of available technology. Regardless of the terminology, the endeavor is underway. The ethical considerations are complex. Do we possess the right to reintroduce species that we ourselves drove to extinction? What is the ultimate purpose? Conservation or spectacle? Where will these resurrected animals reside? Their original ecosystems have transformed, and New Zealand evolved for 6 centuries without the moa. Reintroducing a keystone species into this environment will inevitably trigger cascading effects, some predictable, others not. Colossal contends that de-extinction serves a purpose beyond merely bringing back individual species. It is about developing technologies for genetic rescue. tools that can safeguard critically endangered species before their irreversible disappearance. If genomes can be edited to revive extinct traits, they can also be modified to enhance genetic diversity within endangered populations, eradicate genetic diseases, and adapt species to changing environmental conditions. The Mammoth Project, for instance, is framed as climate intervention. Woolly mammoths were ecosystem engineers. They maintained grasslands by knocking down trees and fertilizing the soil and compacted snow in winter. Their presence sustained the mammoth steppe ecosystem that once covered vast Arctic regions. This ecosystem reflected more sunlight than the boreal forests that replaced it, thereby reducing heat absorption. The theoretical premise is that resurrecting mammoths and reintroducing them to Siberia could help cool the Arctic. This is a highly optimistic scenario. The scale required for a significant climatic impact would be enormous, necessitating hundreds of thousands of mammoths, not mere dozens. Furthermore, the Arctic is warming due to numerous factors far exceeding the absence of the mammoth steppe. However, this exemplifies how proponents of de-extinction frame their work not as playing God, but as ecological restoration, an effort to rectify human-induced damage. Critics argue that the resources allocated to de-extinction could be better utilized to protect existing species through habitat preservation, anti-poaching initiatives, and captive breeding programs for the thousands of species teetering on the brink of extinction. They question the rationale of resurrecting the moa when the kakapo, another iconic New Zealand bird, is on the verge of disappearing, or pursuing extinct megafauna when existing species cannot be saved. Colossal's response is that these technologies are complementary. The genetic tools developed for de-extinction can also benefit conservation efforts. Funding for ambitious projects attracts attention and resources that might not be directed toward traditional conservation work. The publicity surrounding the resurrection of a mammoth can generate public interest in biodiversity that quieter fieldwork might not achieve. Both perspectives hold validity, yet the work continues. The moa genome is currently being sequenced, and gene editing experiments are in progress. If the projected timeline holds, we could witness moa-like birds within a decade, initially in controlled environments, and eventually in the wild, feeding and breeding. These species, erased by human activity, could return due to human technology. While Colossal focuses on reviving extinct species, others are racing to prevent extinctions before they become irreversible. Researchers are cryopreserving a critically endangered tree before it vanishes. This particular tree may not be famous, unlike a giant sequoia or an ancient bristlecone pine, but it plays a vital role within its ecosystem, providing food and habitat. Its loss would have ripple effects throughout the species dependent upon it. Cryopreservation involves freezing tissues at extremely low temperatures, -196 degrees Celsius, achieved with liquid nitrogen, at which biological processes cease. At these temperatures, cells can remain viable indefinitely. This includes seeds, pollen, tissue samples, and even embryos, preserved in frozen storage as a genetic safeguard in the event the living population disappears. Numerous seed banks worldwide undertake this practice, with the Svalbard Global Seed Vault in Norway being the most renowned. Tucked away deep within an Arctic mountain, shielded by its frozen embrace and profound remoteness, lies a vast repository of agricultural insurance. Millions of seed samples from cultivated crops and wild flora. This sanctuary safeguards against the irreversible loss of plant life. Should a crop variety vanish from its natural habitat, be it due to pestilence, climatic shifts, or the ravages of conflict, the meticulously preserved seeds within Svalbard offer the potential for its reestablishment. However, this method proves insufficient for arboreal species. Numerous tree varieties yield seeds incapable of enduring prolonged cryogenic storage. The innovative solution lies in the realm of tissue culture. Small biological samples are procured from living trees, cultivated in laboratory settings, and subsequently subjected to freezing. In times of need, these frozen tissue cultures can be thawed, nurtured into saplings, and reintroduced to their rehabilitated natural environments. This technique has demonstrated efficacy, though not without its imperfections, as some degree of genetic variability is invariably diminished. Nevertheless, it represents a superior alternative to absolute extinction. The urgency of this situation is palpable. Species are succumbing at a pace that outstrips our capacity for study, for the implementation of conservation strategies, and for the natural ecosystem's ability to adapt. Current estimates place the extinction rate at 100 to 1,000 times the natural background rate, the rate that would prevail absent human influence. We are currently witnessing the sixth mass extinction event, distinct in that it is driven by a single species. Climate change acts as a potent accelerant. Ecosystems are undergoing shifts far exceeding the migratory capabilities of their constituent species. Temperature tolerances are being surpassed. Precipitation patterns are becoming unpredictable, essential pollinators are disappearing, and vital food sources are vanishing. Entire ecological networks, painstakingly evolved over millennia, are being fractured within mere decades. The plight of the vanilla orchid serves as a microcosmic illustration with far-reaching consequences. Vanilla, the ubiquitous flavoring, originates from orchids, a significant portion of which depend on specific bee species for pollination. As the climate transforms, the geographic zones where these orchids and their pollinators naturally coexist are being altered. Projections for the year 2050 indicate a severe disruption of this delicate overlap, potentially leaving vanilla orchids without their essential pollinators and vice versa. While the commercial vanilla industry, reliant on manual pollination, may remain unaffected, ensuring the continued availability of vanilla-flavored products like ice cream, the wild genetic diversity, the crucial reservoir of traits that could be leveraged to develop commercial varieties resistant to disease or adaptable to changing climates, is gravely imperiled. This precarious situation, when extrapolated across thousands of intricate species interactions, encompassing predator-prey dynamics, host-parasite relationships, and the symbiotic connection between mycorrhizal fungi and tree roots, paints a sobering picture. Each such relationship represents a critical thread in the intricate tapestry of ecological networks. The severance of sufficient threads inevitably leads to the collapse of the entire network. Ecosystems do not simply degrade. They endure until a crucial threshold is breached, at which point they undergo an abrupt transition to a fundamentally altered, and often significantly simplified and less biodiverse, state. The subsequent efforts at restoration then become exceedingly challenging, if not entirely impossible. The Atlantic Meridional Overturning Circulation, a vital oceanic current system that includes the Gulf Stream, is showing signs of weakening. This is not a matter of conjecture. It is a scientifically measured phenomenon. Instruments monitoring oceanic flow have documented a discernible deceleration. Predictive models suggest that if this weakening surpasses a critical tipping point, a complete collapse of the system could occur, not gradually, but suddenly. The implications of such an event are profound. The Gulf Stream, responsible for transporting warm tropical waters to the North Atlantic, is the reason Europe enjoys comparatively mild winters despite its high latitude. London, for instance, experiences significantly warmer winters than Calgary, despite being located at a more northerly latitude, a phenomenon directly attributable to the Gulf Stream's influence. A collapse of this current would trigger a dramatic alteration of Europe's climate, characterized by harsher winters, modified precipitation patterns, and severe agricultural disruption. Furthermore, sea levels would be impacted. The current's dynamics contribute to the accumulation of water in specific regions. Its absence would result in a redistribution of sea levels, leading to some coastal areas experiencing inundation far exceeding the predictions based on global average sea level rise. The precise location of this tipping point remains unknown, as does the possibility that it has already been crossed. The inherent inertia within the system means that changes initiated today may not manifest their full effects for decades. This temporal lag is the chilling aspect of climate tipping points. By the time their consequences are evident, it is too late to avert them, leaving only the necessity of adapting to their repercussions. And these repercussions are already beginning to surface. Iceberg A23A, once the world's largest, is now fragmenting. After calving from Antarctica years ago and drifting across the Southern Ocean, its slow melting has accelerated due to increased surface area exposed to warmer waters. While this particular iceberg's disintegration has a negligible impact on sea level, as it was already afloat, it serves as a potent indicator of instability. Antarctic ice is proving increasingly fragile. Glaciers are accelerating their flow, and the ice shelves that buttress them are thinning. West Antarctica, in particular, exhibits pronounced vulnerability. A significant portion of its ice sheets rests on bedrock situated below sea level. This allows warm ocean currents to infiltrate from beneath, initiating a process of melting from below. Once this subice melting commences, it becomes exceedingly difficult to arrest. The ice sheet becomes unanchored, surrenders to gravity, and slides towards the ocean, ultimately disintegrating. The ice contained within West Antarctica alone possesses the capacity to elevate global sea levels by over 3 meters or 10 feet. While this catastrophic rise is unlikely within the current decade, or even this century, it represents a plausible threat on a timescale that is remarkably short when compared to the enduring presence of coastal metropolises. Cities such as New York, London, Shanghai, Mumbai, and Bangkok are already engaged in planning for futures marked by substantially higher sea levels. Permafrost represents another critical tipping point. The Arctic is experiencing warming at a rate exceeding that of any other region on Earth. Permafrost, ground that has remained frozen for millennia, is now thawing. Encapsulated within this thawing permafrost is vast quantities of organic matter. the remnants of ancient plant and animal life, frozen before decomposition could occur. As the permafrost thaws, microbial activity is reawakened, leading to the release of carbon dioxide and methane. Methane, a greenhouse gas significantly more potent than carbon dioxide in its heat-trapping capacity over shorter time frames, creates a perilous feedback loop. Warming thaws permafrost. The thawing releases greenhouse gases. These gases exacerbate warming, which in turn thaws more permafrost. The crucial unknown variables are the rate at which this process unfolds and the sheer volume of carbon that will be released. Estimates vary considerably, ranging from a slow, incremental addition to atmospheric carbon in the most optimistic scenarios, to a rapid and massive release that could dwarf any reductions achieved in fossil fuel emissions in the worst-case projections. Continuous monitoring through instruments deployed across the Arctic provides data on soil temperatures, methane emissions, and vegetation changes. The current data indicates that the thawing process is indeed underway, though not yet at a catastrophically rapid pace. However, the persistent concern is that a certain threshold could be crossed, triggering a significant acceleration. This could manifest through rapid thaw events, where the ground collapses as underlying ice melts, leading to the formation of lakes in permafrost regions that accelerate heat transfer. Furthermore, wildfires, increasingly common, can consume newly thawed organic matter, releasing substantial amounts of carbon instantaneously. The proliferation of wildfires is not confined to the Arctic. It is a global phenomenon, driven by hotter temperatures, drier conditions, an abundance of dead vegetation serving as fuel, fire seasons that begin earlier and conclude later, and fires igniting in regions previously unaccustomed to such events. The resultant smoke plumes can degrade air quality across thousands of kilometers, while the carbon released represents a significant contribution to atmospheric loading. The loss of forests, crucial carbon sinks, further exacerbates the problem by reducing the planet's capacity to absorb carbon dioxide, creating yet another detrimental feedback loop. The hurricane season in the Atlantic is intensifying, with an increased frequency of Category 4 and 5 storms. These powerful storms are fueled by warm ocean waters, and as the oceans continue to warm, hurricanes gain access to more energy. This translates into faster intensification, greater rainfall due to warmer air's increased moisture-holding capacity, and longer durations as atmospheric steering patterns become disrupted. Coastal communities are facing escalating risks, prompting insurance companies to withdraw from high-risk areas and leading to declining property values in flood-prone zones. The concept of managed retreat, the planned abandonment of vulnerable coastlines, has transitioned from a theoretical discussion to a pragmatic necessity. All these interconnected phenomena, climate shifts, species extinction, and ecosystem collapse, are not isolated issues, but rather interconnected facets of a single, overarching crisis. This crisis is fundamentally driven by human activities over the past 2 centuries, including the combustion of fossil fuels, extensive deforestation, and the large-scale alteration of landscapes. We have inadvertently reshaped the Earth's atmospheric composition and disrupted its thermal equilibrium. In response, the planet is reacting, not with malice or intent, but through the immutable laws of physics, chemistry, and biology, responding to fundamental shifts in its boundary conditions. The recent decline in China's emissions offers a small ray of hope, demonstrating that change is indeed achievable and that economic progress and emission reductions can occur concurrently. However, the emissions reduction of one nation in a single year does not constitute a sustained trend. Global emissions continue their upward trajectory, and atmospheric carbon dioxide levels persist in their climb. We remain on a path towards significant global warming. The impacts we are currently observing, the escalating wildfires, the intensified hurricanes, and the accelerating ice melt, are direct consequences of approximately 1.2 degrees Celsius of warming above pre-industrial levels. We are already committed to further warming. Even if emissions ceased entirely today, the planet's climate would continue to warm for decades due to the inherent inertia of the Earth system. The Paris Agreement's objective of limiting global warming to 1.5 degrees Celsius now appears increasingly unattainable. Achieving a 2-degree limit may still be feasible with aggressive and decisive action. Beyond 2 degrees of warming, the risks escalate dramatically, increasing the probability of crossing more tipping points, making adaptation progressively more challenging, driving up costs, and exacerbating human suffering. Consequently, we find ourselves at a peculiar juncture. We possess the capacity for remarkable technological feats, including the potential resurrection of extinct species, the generation of fusion energy, and the construction of quantum computers, yet we struggle to effectively address the consequences of our own unprecedented success. The very ingenuity that propelled the development of industrial civilization is now being mobilized to prevent that civilization from destabilizing the natural systems upon which it critically depends. Perhaps this represents the ultimate test, not our ability to engineer impressive technologies, which is clearly evident, but our capacity to deploy these technologies judiciously, to foster global cooperation in resolving transboundary issues, to adopt a temporal perspective that extends beyond the confines of election cycles or quarterly financial reports, and to accord the same value to our forests, oceans, and atmosphere as we do to the pursuit of gross domestic product growth. China's reduction in emissions, while a minor triumph in a larger conflict, signifies progress. Should the mower, a hypothetical technology, be successfully resurrected, it would represent another incremental victory. However, these individual successes are insufficient on their own. The current trajectory requires a more pronounced and accelerated shift. This necessitates a greater number of nations emulating China's commitment to renewable energy expansion, an increased number of species being preserved before the necessity of de-extinction arises, and a level of political will commensurate with the magnitude of the challenge. It is October 2025. The planet continues to warm, species vanish, ecosystems are stressed, and humanity, in a slow and uneven manner, begins to respond. While the urgency displayed is not commensurate with the gravity of the situation, it is greater than in previous times. The fundamental question remains, is this slow and uneven response adequate, or are we rapidly approaching a point of no return, beyond which irreversible damage cannot be averted? Chapter 7 delves into the medical breakthroughs of 2025, a 75% slowdown in disease progression. This is the remarkable achievement of a new gene therapy targeting Huntington's disease. This represents a 75% reduction in the advancement of a condition that has, until this point, been a terminal diagnosis with no prospect of intervention. Huntington's disease is characterized by a unique cruelty. It waits. Individuals may carry the causative gene throughout their childhood and into their 20s and 30s, living entirely normal lives. Then, typically in their 40s, symptoms begin to manifest. These include involuntary movements, cognitive decline, and psychiatric disturbances. Over the subsequent 10 to 20 years, the disease systematically degrades motor control, memory, and personality. Previously, there was no known cure, nor any treatment capable of significantly slowing its progression. UK physicians published their findings in September, detailing a therapy that directly targets the Huntington gene. Huntington's disease arises from a mutation within this gene, specifically an excessive repetition of a particular DNA sequence. The greater the number of these repeats, the earlier the onset of symptoms and the faster the disease progresses. The mutated gene produces a toxic protein that accumulates within brain cells, particularly in the regions responsible for controlling movement and cognition. This cellular damage leads to cell death and the degeneration of brain tissue, resulting in a loss of function. The gene therapy approach employs antisense oligonucleotides, short, synthetic DNA fragments designed to bind to the messenger RNA produced by the Huntington gene. This binding action prevents the RNA from being translated into protein. Consequently, a reduction in the toxic protein leads to diminished cellular damage and a slower disease progression. A significant challenge lies in the delivery of this therapy to the brain, necessitating its passage across the blood-brain barrier and into the specific cells undergoing degeneration. The UK team successfully addressed this hurdle through intrathecal injection, administering the therapy directly into the cerebrospinal fluid that surrounds the brain and spinal cord. From this location, the therapeutic agent diffuses into the brain tissue. It is important to note that this treatment is not permanent. The antisense oligonucleotides degrade over time, requiring patients to undergo repeated administrations. However, if these subsequent doses can be administered safely, if the observed 75% slowdown is replicated in larger clinical trials, and if side effects remain manageable, this therapy has the potential to transform Huntington's disease from a rapidly fatal condition into a slowly progressive one that can be managed. For families affected by Huntington's, this development holds immense significance. The disease follows an autosomal dominant inheritance pattern, meaning that if one parent carries the mutation, each child has a 50% probability of inheriting it. Consequently, many individuals at risk opt against genetic testing, preferring not to know their predetermined fate. However, the existence of a viable treatment alters this calculus. Knowing one's status then becomes less about confronting an unavoidable doom and more about enabling proactive intervention through early treatment. Type 1 diabetes is also showing promising avenues for improvement. A small trial involving only 12 patients has yielded striking results, with 10 of them no longer requiring supplemental insulin a full year after treatment. Type 1 diabetes is an autoimmune disorder wherein the immune system mistakenly attacks the insulin-producing beta cells within the pancreas. A deficiency in insulin leads to uncontrolled blood sugar levels, necessitating lifelong insulin injections, meticulous dietary management, and constant blood glucose monitoring. While manageable, this regimen is arduous, and despite optimal care, long-term complications such as nerve damage, kidney disease, and vision problems remain common. The cellular therapy approach takes a different strategy, focusing not on suppressing the autoimmune response, but on replacing the destroyed beta cells. Stem cells are carefully guided in the laboratory to differentiate into insulin-producing cells. These manufactured cells are then enclosed within a protective implant designed to allow the diffusion of nutrients, oxygen, and insulin, while simultaneously preventing the infiltration of immune cells. This encapsulation ensures that the newly implanted beta cells can produce insulin without being subjected to immune attack. The outcome of 10 out of 12 patients becoming insulin independent after 1 year is not a mere statistical anomaly. It strongly suggests the efficacy of this approach. The remaining 2 patients, while still requiring some insulin, have demonstrated reduced needs, indicating that their implanted beta cells are functioning, albeit not yet at full capacity. Larger trials involving hundreds of patients are already in the planning stages, with extended follow-up periods to assess the long-term persistence of the treatment's effects, its potential to prevent complications, and its viability as a standard therapeutic option. Imagine a child diagnosed with type 1 diabetes being offered a definitive solution, a single procedure that eliminates the need for daily injections and constant vigilance, allowing for a normal life. While this future is not yet fully realized, it is now a discernible prospect on the horizon. The progress is sufficiently advanced that parents of newly diagnosed children are inquiring with their physicians about delaying treatment to await the availability of this cellular therapy. Furthermore, psilocybin, a psychedelic substance, is demonstrating the capacity to alleviate anxiety for extended periods, with a single dose providing relief for months. This finding originates from a rigorously controlled clinical trial, not from anecdotal accounts. Participants suffering from anxiety disorders that significantly impair their quality of life received a single dose of psilocybin within a therapeutic setting, supervised by trained therapists and supported by integration sessions designed to help process the experience. 6 months post-treatment, the majority of participants exhibited a substantial reduction in anxiety symptoms. This effect is not characterized by temporary relief or a fleeting sense of euphoria. Rather, it represents a lasting alteration in how their brains process fear and worry. Psychedelics are experiencing a resurgence in psychiatric applications, not due to fleeting trends or cultural nostalgia, but because of their demonstrable efficacy. MDMA shows promise for treating post-traumatic stress disorder, psilocybin for depression, and ketamine for treatment-resistant cases. When administered therapeutically, these substances achieve outcomes that conventional medications often struggle to match, and they do so with single or limited doses, rather than daily prescriptions taken over extended periods. While the precise mechanisms are still under investigation, a clear pattern is emerging. Psychedelics enhance neuroplasticity, rendering the brain temporarily more malleable. This increased plasticity allows for the disruption of ingrained patterns of thought, such as rumination loops, anxiety spirals, and depressive cognitions, which become less rigid. Consequently, new, healthier patterns of thinking and feeling can be established. The therapeutic support provided during and after the psychedelic experience is crucial in solidifying these beneficial changes. The psychedelic substance itself is not the sole treatment. It acts as a catalyst, amplifying the effectiveness of therapy. Psilocybin's application for anxiety aligns with this model. The psychedelic experience, while often intense and occasionally challenging, is not inherently therapeutic in a simplistic sense. It serves to disrupt the neural circuitry associated with anxiety, providing individuals with a novel perspective, the realization that their anxiety is not an immutable aspect of their personality, but rather a learned pattern of brain activity, and that such patterns are amenable to change. The medical establishment is gradually acknowledging these findings. The Food and Drug Administration is reviewing applications for MDMA-assisted therapy, and psilocybin has been granted breakthrough therapy designation for depression. Clinics offering ketamine treatment are becoming increasingly prevalent. While these treatments remain tightly regulated and necessitate the involvement of trained therapists and medical supervision, they have moved beyond the fringes and are now recognized as legitimate medical interventions. Cystic fibrosis represents another disease where the treatment trajectory has significantly improved. A new medication has extended the life expectancy of patients by decades. Cystic fibrosis is a genetic disorder that affects the lungs and digestive system, characterized by the accumulation of thick, viscous mucus. This mucus obstructs the airways, trapping bacteria and leading to chronic infections. Patients traditionally undergo daily chest physiotherapy to clear the mucus, require frequent antibiotic treatments, and experience a gradual decline in lung function. Historically, most individuals diagnosed with cystic fibrosis did not survive beyond their 30s. The advent of CFTR modulators marked a turning point. These drugs target the defective protein responsible for the disease. While they do not provide a cure, as the underlying genetic defect persists, they restore sufficient protein function to normalize mucus consistency. This leads to a reduction in lung infections and improved nutrient absorption, enabling patients to live longer, healthier lives. The most recent modulator, lauded for its efficacy, has pushed life expectancy into the 60s and beyond. Individuals with cystic fibrosis now have the potential to pursue careers, raise families, and enjoy retirement, prospects that were unimaginable for previous generations. However, the exorbitant cost of this drug presents a significant ethical challenge. This exorbitant expense represents the darker side of medical progress, with life-saving treatments priced beyond the reach of many individuals. While insurance coverage exists in wealthier nations, equitable access remains a critical issue, and patients in developing countries often face insurmountable financial barriers to obtaining these life-altering medications. The scientific advancements in this field are outpacing the economic mechanisms required for widespread accessibility. In parallel, a completely unforeseen discovery has emerged. Accutane, a medication primarily used to treat acne, may have the potential to restore sperm production in infertile men. This outcome was not the intended result of a clinical trial specifically designed to assess fertility. Rather, it was an observational finding. Men undergoing treatment with Accutane for severe acne reported noticing improvements in their sperm counts, observations that were subsequently noted by their physicians. This led to formal scientific investigation, which has indeed indicated a potential therapeutic effect. Although the study is small and the results are preliminary, if they are substantiated, it represents a remarkable and unexpected benefit. Accutane is a retinoid, a class of compounds that influence cell differentiation and growth. While best known for its dermatological application in reducing oil production in the skin, it also impacts other tissues, apparently including the cells responsible for sperm generation. Male infertility is a prevalent condition, often poorly understood, with many cases classified as idiopathic, meaning no clear cause is identified and no effective treatment exists. If a drug already approved and widely prescribed proves effective for this condition, it would be a significant and fortunate discovery. Science is replete with such serendipitous breakthroughs. Penicillin, for example, was discovered when a mold accidentally contaminated a bacterial culture. Viagra, initially developed as a cardiovascular medication, was found to have other physiological effects. Minoxidil, originally prescribed for high blood pressure, was observed to promote hair growth as a side effect, leading to its development as a treatment for baldness. Researchers pursuing one objective often stumble upon unexpected and valuable findings. This underscores the paramount importance of basic research and the value of exploring biological phenomena without a predetermined application in mind, as one never knows what groundbreaking discoveries might emerge. Artificial intelligence is now beginning to predict medical outcomes years in advance, surpassing the capabilities of human physicians. A system trained on routine blood test data has demonstrated the ability to identify patterns associated with recovery from spinal cord injuries, patterns that are imperceptible to human analysis due to their complexity and the subtle interplay of numerous variables. The AI identifies correlations between specific combinations of protein levels, cell counts, and metabolic markers, enabling it to predict an individual's likelihood of regaining function. Crucially, these algorithms can identify these patterns without necessarily elucidating the underlying causal mechanisms. The correlations are black boxes, yet their predictive accuracy lends them utility. For instance, healthcare professionals can now customize rehabilitation regimens, establish grounded expectations for patients, and allocate resources judiciously towards individuals with the highest likelihood of positive outcomes. Another artificial intelligence system, this one focused on analyzing neurological imaging, possesses the capacity to forecast the onset of blindness years before any physical manifestations emerge. Conditions such as diabetic retinopathy, macular degeneration, and glaucoma all involve a progressive accumulation of damage during their nascent stages, a phase where vision remains unimpaired. Early detection through such advanced AI screening tools could become a standard practice in healthcare. The vision is for everyone to undergo brain scans, with AI identifying those at elevated risk for closer monitoring and proactive treatment initiation at the earliest indication of trouble, representing a paradigm shift towards precision medicine. This approach moves away from relying on population averages towards making individual-level predictions, and from reacting to disease after its symptoms appear to preventing it before it ever takes root. The foundation for this personalized approach was laid by genomics. Recognizing that each individual possesses a unique genetic makeup, varying predispositions to illness, and distinct responses to pharmacological interventions, genome sequencing allows physicians to tailor treatments accordingly. Integrating this genetic information with lifelong medical records, data from wearable sensors, and sophisticated AI analysis further refines medicine into a truly personalized experience. However, the implementation of such advanced diagnostics, including widespread brain scanning and genome sequencing, is inherently costly. AI systems demand substantial data, significant computational power, and specialized expertise, making them highly effective within affluent nations possessing robust healthcare infrastructures. Their utility diminishes considerably in regions grappling with fundamental medical necessities, thereby widening the chasm between potential advancements and actual accessibility. While technological progress accelerates, policy, economic considerations, and equitable access unfortunately lag behind. Nevertheless, the overarching trajectory of medical advancement is undeniable, leading to interventions that were once considered beyond imagination. This includes gene therapies, cell therapies, psychedelic-assisted therapies, and AI-driven diagnostics. The focus has shifted from merely alleviating symptoms to addressing the root causes of ailments, such as correcting faulty genes, regenerating damaged tissues, and recalibrating aberrant neural pathways. Certain maladies, however, remain stubbornly resistant to treatment. Alzheimer's disease, for example, continues to be a devastating condition, with current treatments offering only marginal deceleration of its progression despite decades of intensive research and billions in investment. Cancer, while increasingly managed through early detection and targeted therapies, still poses a lethal threat. Chronic pain management remains largely inadequate, and while mental health treatments provide relief for many, they fall short for a significant portion of the population. The roster of unresolved medical challenges is extensive, yet so too is the list of recently overcome obstacles. Diseases once deemed untreatable are becoming manageable, and conditions that previously led to premature mortality now permit extended lifespans. Notable achievements include a 75% slowdown in Huntington's disease progression, the potential for a cure for type 1 diabetes through cell therapy, months of anxiety relief from a single dose of LSD, and cystic fibrosis patients now living into their 60s. Each of these breakthroughs, though incremental, builds upon foundational work spanning decades, collectively signifying a profound transformation in the capabilities of medicine. Furthermore, the pace of innovation is escalating, with an increasing number of therapeutic targets being identified, more treatments entering development, and a greater array of sophisticated tools becoming available. Technologies like CRISPR are standardizing gene editing, stem cell techniques are continually improving, and AI is adept at deciphering complex patterns within vast datasets that elude human perception. The infrastructure supporting biomedical research, encompassing laboratories, instruments, databases, and computational tools, is progressively enhancing its capacity year by year. By October of 2025, significant advancements were announced: a 75% reduction in Huntington's disease progression, 10 out of 12 diabetes patients rendered insulin independent, lasting anxiety relief demonstrated by LSD, and drug treatments for cystic fibrosis gaining widespread recognition. Additionally, Accutane is showing promise in improving male fertility, and AI is proving effective in predicting blindness years in advance. While each success story is individual, a broader perspective reveals a consistent pattern. Medicine is experiencing a golden age of discovery. This is not attributable to a single miraculous drug, but rather to the entire system's capacity to generate breakthroughs at an unprecedented rate, exceeding our current ability to fully integrate them. The primary challenge now lies in the dissemination of these advancements, ensuring that every individual in need receives access to these treatments, making them economically viable, and adequately training the healthcare professionals required for their administration. This necessitates the development of suitable clinics, manufacturing facilities, and robust supply chains. Science is currently outpacing its practical implementation. We possess the knowledge to perform certain procedures, but lack the scaled infrastructure to do so universally. This, however, is a favorable predicament, preferable to ignorance or encountering insurmountable obstacles. Nevertheless, it remains a challenge that demands more than scientific ingenuity. It requires effective policy, sound economic strategies, and collective societal will, a commitment to ensure that medical progress benefits all, not merely those with the financial means. The goal is for the breakthroughs of 2025 to become standard medical practice by 2035, ushering in an era where disease and suffering are reduced for the global population. Chapter 8. Space discoveries are accelerating. 6000. That is the current count of confirmed exoplanets discovered orbiting stars beyond our solar system, 6,000 worlds outside our own. This milestone was reached on September 17, 2025, yet it passed with less fanfare than might be expected, as identifying exoplanets has become a routine occurrence, with dozens identified each month. The prevailing question has shifted from the mere existence of planets around other stars to their nature, the prevalence of Earth-like worlds, and the potential for extraterrestrial life. The 6,000th exoplanet identified is not particularly remarkable. It is a gas giant orbiting a sun-like star approximately 800 light-years away, classified as a hot Jupiter. These are celestial bodies comparable in size to Jupiter, yet they orbit extremely close to their parent stars, so near that their atmospheric layers are being eroded by stellar radiation. Beneath their gaseous exteriors, their surfaces, if they exist, are heated to thousands of degrees. While not candidates for life or suitable for colonization, they are invaluable for understanding planetary formation processes, specifically how such massive planets end up so close to their stars, whether they formed there or migrated inwards. The first exoplanet was confirmed in 1995, and it has taken 30 years to reach the count of 6,000, a testament to exponential growth. Initial discoveries were slow due to the inherent difficulty of detecting exoplanets, as they do not emit light but merely reflect the faint glow of their stars, and they are minuscule in comparison. Observing a planet next to its star is akin to spotting a firefly beside a searchlight from thousands of kilometers away. Consequently, indirect detection methods are employed. The transit method monitors for slight dips in a star's luminosity as a planet passes in front of it. If the planet's orbital plane aligns with our line of sight, regular reductions in brightness are observed. The magnitude of this dimming indicates the planet's size, while the frequency of these dips reveals its orbital period. The radial velocity method measures the subtle wobble of a star caused by the gravitational influence of orbiting planets. As a planet orbits, it exerts a slight tug on its star, pulling it periodically towards and away from us. This gravitational tug results in a Doppler shift in the star's light, appearing as a red shift when moving away and a blue shift when moving towards us. While effective, these methods are inherently biased. The transit method favors planets with orbits aligned with our observational perspective, while the radial velocity method is more sensitive to massive planets in close proximity to their stars due to the larger stellar wobbles they induce. Detecting smaller, more distant planets remains challenging, and even finding Earth itself from another star system using these techniques would be difficult. Therefore, the 6,000 exoplanets detected thus far do not represent a statistically unbiased sample. They are primarily those easiest to detect. The Vera C. Rubin Observatory, which commenced operations in late 2025, is poised to change this landscape. This is not a space-based telescope, but a terrestrial facility situated in Chile, boasting an 8.4-meter mirror and a 3.2 billion pixel camera, the largest digital camera ever constructed for astronomical purposes. Its exceptionally wide field of view allows it to capture images of the entire observable sky every few nights. The observatory's objective is to generate a comprehensive movie of the universe, observing all celestial phenomena to detect changes. For exoplanet science, this translates to detecting planets through microlensing. This phenomenon occurs when a star passes between our line of sight and a more distant background star, its gravity acting as a lens and briefly magnifying the background star's light. If the intervening star hosts planets, they introduce their own minute lensing signatures. While such events are infrequent for any single star, the Rubin Observatory's continuous, all-sky monitoring transforms these rare occurrences into statistically significant detections. Crucially, microlensing is sensitive to planets located at any orbital distance, including cold, distant worlds that are often missed by transit and radial velocity methods. The Rubin Observatory is anticipated to discover thousands, potentially tens of thousands, of exoplanets. It will also identify asteroids, supernovae, black holes, counterparts to gravitational wave events, and near-Earth objects, essentially anything that moves or changes in the celestial sphere. The data generated will be staggering, amounting to 15 terabytes per night, every night, for a decade. This necessitates the utilization of artificial intelligence and machine learning, as human capacity is insufficient to process such volumes of information. Algorithms will sift through the data, flagging noteworthy events for further investigation. While the Rubin Observatory observes from Earth, space telescopes are dedicated to probing exoplanet atmospheres. The James Webb Space Telescope, JWST, has been instrumental in analyzing the light that traverses exoplanet atmospheres during transits. As a planet passes in front of its star, a portion of the star's light filters through the planet's atmosphere before reaching Earth. Different molecules absorb specific wavelengths of light, leaving distinct spectral fingerprints. These spectra can reveal the presence of water vapor, carbon dioxide, methane, ammonia, and even potential biosignature gases like oxygen or phosphine. In September, astronomers announced the detection of oxygen in the atmosphere of the most distant galaxy ever confirmed, JADES, GSZ 140. This galaxy is located 13.4 billion light-years away, meaning we are observing it as it was only 400 million years after the Big Bang, a period when the universe was young, stars were just beginning to form in large numbers, and yet oxygen was already present. Oxygen is generated within stars through nuclear fusion and is released during the explosive death of massive stars as supernovae. Its detection at such an early cosmic epoch indicates that stellar evolution was already well advanced, with multiple generations of stars having completed their life cycles and enriched the cosmos with heavier elements. This particular oxygen detection is unrelated to life. It predates the existence of biology by a significant margin. Instead, it provides crucial insights into the chemical enrichment of the universe, the rate at which stars formed and evolved, and how the fundamental building blocks for planets and, eventually, life became available. Earth's composition primarily consists of oxygen, silicon, iron, and other elements heavier than hydrogen and helium, all of which were synthesized within stars. The assertion that we are made of stardust is not a mere poetic metaphor, but a literal scientific fact, and the JWST is illuminating the processes by which this cosmic alchemy occurred in the universe's infancy. Closer to home, Neptune's auroras were captured photographically for the first time. Auroras occur when charged particles from the solar wind interact with a planet's magnetic field, are channeled towards the poles, and excite atmospheric atoms. On Earth, these phenomena are known as the northern and southern lights. While common on Jupiter and Saturn, Neptune's extreme distance from the Sun results in faint auroras. The Hubble and JWST, through a combined effort of visible and infrared observations, successfully imaged these elusive displays. The significance of this achievement lies in what auroras reveal about a planet's magnetic field and atmospheric composition. Neptune's auroras have shown that its magnetic field is offset from its rotational axis, being both tilted and displaced. This is an unusual characteristic, as most planets exhibit magnetic fields that are roughly aligned with their rotation. Neptune's field is observed to be messy and complex, and understanding the reasons behind this asymmetry helps us comprehend planetary interiors. Magnetic fields are generated by dynamos operating within the liquid, electrically conductive layers deep within planets. Neptune's offset field suggests anomalies in its internal structure, possibly involving layering of different materials or non-symmetric convection patterns. These detailed observations are vital for refining our models of planetary formation, particularly concerning ice giants, how they form, why they are common around other stars but rare in our solar system, and what factors determine the development of a strong magnetic field. Neptune serves as our most accessible analog, and studying it informs our understanding of thousands of ice giant exoplanets. A new quasimoon was discovered orbiting within Earth's vicinity. Quasimoons are not true satellites of Earth. Rather, they orbit the Sun, but their orbits are synchronized with Earth's in such a way that they appear to accompany us. From our perspective on Earth, they seem to orbit our planet, when in reality, they are following their own solar trajectories that happen to resonate with ours. This particular quasimoon has likely been present for decades, perhaps longer, but has only recently been detected. This discovery underscores how much remains unknown about our immediate cosmic neighborhood. Near-Earth objects, including asteroids and comets, are small celestial bodies that pass close to Earth or share its orbital space. The majority pose no threat, but some are potentially hazardous. These objects are continuously tracked, cataloged, and their orbits calculated to ensure they are not on collision courses with Earth. Despite these efforts, new discoveries continue to be made, highlighting the sheer abundance of celestial rocks and the incompleteness of our current surveys. This emphasizes the critical importance of comprehensive sky survey projects like the Rubin Observatory, which aim to identify all celestial bodies down to a certain size and meticulously map their orbits to predict potential encounters decades in advance. Effective planetary defense hinges on accurate detection and tracking. It is impossible to deflect an asteroid if its approach is not foreseen. We possess the technological capability to deflect asteroids, employing methods such as kinetic impactors, gravity tractors, and, in worst-case scenarios, nuclear options. The primary challenge, however, lies in detection and tracking. China is making significant advancements in space exploration, with its stated objective being the return of Martian samples to Earth for laboratory analysis, going beyond mere robotic exploration. This mirrors NASA's Perseverance mission, which has encountered funding difficulties. China perceives this as an opportunity. Successfully executing a Mars sample return mission ahead of NASA would represent a major triumph in terms of prestige, technological demonstration, scientific achievement, and geopolitical influence. However, a critical concern arises regarding containment. When bringing samples back from another planet, it is imperative to ensure they do not contaminate Earth. The likelihood of Martian life existing is low, and the probability of that life being hazardous to Earth is even lower, though not zero. Protocols are in place for such scenarios. Sample return capsules are designed to be hermetically sealed and are only opened within specialized biosafety facilities. The samples are then subjected to quarantine and analyzed. Only after confirming their safety are they released for broader scientific study. The crucial question is whether China will adhere to these protocols, permit international inspection of its containment procedures, and share data regarding the samples, or if it will maintain exclusive control over the process behind closed doors. The global scientific community is observing these developments closely, and offers of collaboration have been extended, as samples analyzed by laboratories worldwide would possess greater scientific value. However, space programs are also strategic assets, and technologies developed for sample return can have dual applications, including military and geopolitical leverage. China may opt for an independent approach. Meanwhile, NASA's budget is facing considerable pressure, with proposed cuts threatening science missions. While the Europa Clipper, designed to study Jupiter's moon Europa, was successfully launched, the feasibility of subsequent missions remains uncertain. The Mars Sample Return Initiative, already experiencing difficulties, faces further delays or potential cancellation. The Artemis program, aimed at returning humans to the moon, is consuming significant resources. Manned missions are inherently expensive, and while political support for them exists, it often comes at the expense of robotic scientific endeavors. This represents a perpetual tension in space exploration. Robotic missions are cost-effective and capable of venturing into environments inaccessible to humans, eliminating the need for life support, sustenance, and return journeys. However, humans possess a unique capacity to inspire public interest in ways that robots cannot. The Apollo missions captivated the world, and while the Perseverance rover is scientifically invaluable, it does not generate the same level of public excitement. Consequently, funding often gravitates towards human spaceflight, even when robotic missions might yield more scientific return per dollar invested. The Trump administration's Big, Beautiful Bill advocates for manned lunar missions, yet proposed budget reductions place NASA's scientific initiatives at risk. The Artemis program receives funding, while Earth science satellite missions are subject to cancellation. This reflects a deliberate choice, a statement of priorities. Space is viewed either as a domain for human presence or as a laboratory for understanding the universe. Both perspectives hold significant value and warrant support, but finite budgets necessitate difficult choices. The commercial space sector is beginning to fill certain voids. Companies such as SpaceX, Blue Origin, and Rocket Lab are actively launching satellites, constructing infrastructure, and offering services previously monopolized by NASA. This trend is beneficial for cost reduction and fostering innovation. However, commercial enterprises tend to focus on profitable activities, including communication satellites, Earth observation, and space tourism. Scientific missions that do not generate revenue still require government funding. The private sector is unlikely to undertake missions to study Neptune's auroras or collect ice samples from Enceladus. These endeavors remain the purview of government agencies. 50 years ago, NASA dispatched 2 spacecraft, the Viking missions, to search for life on Mars. The findings from these missions continue to be a subject of discussion. The biological experiments yielded ambiguous results. Some tests indicated microbial activity, while others did not. The prevailing scientific consensus suggests that these results were likely chemical in nature rather than biological. However, lingering doubts persist. What if the Viking missions actually detected Martian microbes, and we dismissed the evidence? What if the experiments were not designed to identify the specific forms of life present on Mars? This is precisely why sample return is so crucial. Bringing Martian rocks back to Earth allows for analysis using every available tool, subjecting them to tests that Viking could not perform, and searching for isotopic signatures, organic molecules, cellular structures, and any other definitive evidence. The leopard spot-like formations observed in Perseverance's sample from Sapphire Canyon are tantalizing, but tantalizing is not definitive. We require the actual samples, and it is imperative to obtain them before any other nation does. If China successfully returns Mars samples first, they will author the initial chapter of this scientific narrative, receiving both credit and setting the global perception. From a purely scientific standpoint, the identity of the entity returning the samples should be secondary to the fact that samples are returned and their findings are shared. However, from a geopolitical perspective, this is of immense importance. Space is increasingly becoming a contested domain, not only scientifically but also strategically. Satellites are indispensable for modern military operations, encompassing communication, navigation, and reconnaissance. Space debris poses a growing problem, with an excessive amount of junk in orbit leading to collisions that generate further debris, potentially rendering certain orbital paths unusable. Treaties govern space activities, but their enforcement is often weak. The Outer Space Treaty, drafted in 1967, stipulates that space is for peaceful purposes and prohibits weapons of mass destruction in orbit. However, the modern space environment is vastly more complex. Nations such as China, the United States, Russia, and India have demonstrated anti-satellite capabilities, and the destruction of satellites generates debris fields that threaten other orbiting assets. This presents a significant challenge with no easy solutions. Effective cleanup of space debris is not feasible. Efforts are focused on mitigation strategies, such as designing satellites for deorbiting at the end of their operational life, tracking debris, and maneuvering active satellites to avoid collisions. The fundamental issue, however, is that space is becoming increasingly crowded, and there is no global governing body to manage traffic effectively. The International Space Station is nearing the end of its operational lifespan, having exceeded its design parameters. Systems are experiencing wear and tear, requiring constant maintenance. Its future remains uncertain, with Russia having expressed intentions to withdraw and budget constraints making a replacement unlikely. Commercial space stations are being proposed by entities like Axiom and Orbital Reef, but these projects are years away from completion and depend on sustained funding. The loss of the ISS would represent a setback for space research, though not a catastrophic one, as many of its functions could potentially be replicated on commercial stations or robotic platforms. However, the ISS holds symbolic significance as a testament to international cooperation and continuous human presence in space for over 2 decades. Its decommissioning would carry a weight beyond its practical implications. Nevertheless, space exploration continues unabated, with missions launching and discoveries accumulating. The confirmation of the 6,000th exoplanet marks another milestone in this ongoing endeavor. Oxygen has been identified in the very first galaxies. The planet Neptune's auroras have now been captured in photographs. New celestial bodies orbiting a quasar have been discovered. Plans are in motion, though their realization is yet to be determined, for a mission to bring samples back from Mars. The Vera Rubin Observatory is preparing to commence its operations. The James Webb Space Telescope is currently unveiling the universe in infrared light. Commercial entities are engaged in establishing infrastructure, while government organizations are actively pushing the frontiers of exploration. Space is immense, astonishingly so, and our journey of discovery within it has only just begun. 6,000 exoplanets might sound like a considerable number, but this figure diminishes when one considers that our own galaxy alone likely harbors trillions. We have managed to approach a mere handful of celestial bodies within our solar system. Yet, there are hundreds more that we have only managed to observe fleetingly. We have successfully landed on the Moon and Mars, as well as Venus, Titan, various asteroids, and comets. While we have conducted flybys of most of the planets, vast expanses of space remain uncharted. The coming decades are slated to feature missions targeting worlds believed to possess liquid water or methane beneath their icy surfaces, such as Europa, Enceladus, and Titan. These are locations where chemical processes may be occurring, and where life in unimaginable forms might potentially exist. We anticipate more ambitious Mars expeditions, including human landings, possibly leading to permanent settlements. The concept of in situ resource utilization, employing Martian materials for the production of fuel, water, and construction supplies, will likely be explored. Furthermore, attempts at asteroid mining, moving beyond the realm of science fiction, are on the horizon. Actual companies with concrete strategies are planning to extract water and valuable metals from asteroids located near Earth. The economic viability and technological challenges are significant, but the potential resources are undeniable. Asteroids contain platinum group metals in concentrations substantially higher than those found in Earth's crust. Water can be electrolyzed into hydrogen and oxygen, providing rocket fuel. If the cost of extraction can be reduced, space-based resource procurement becomes a practical prospect. We will continue to discover exoplanets, not exclusively gas giants, but also rocky worlds, super-Earths, numerous Neptune-like planets, and eventually, true Earth analogs. These would be planets of appropriate size, situated at suitable distances from their stars, possessing atmospheres that exhibit evidence of water vapor and oxygen. And perhaps, just perhaps, we might find something that hints at the presence of life. The universe is vast. If life exists beyond Earth, it is likely widespread. We simply have not detected it yet. However, our observational tools are improving annually, and our search is gaining momentum. Chapter 9. Biology defying its own parameters. An ant species originating from Europe has been observed to clone individuals belonging to an entirely different species. To reiterate, it is not reproducing its own kind through cloning, but rather producing genetic duplicates of another species altogether. As one researcher aptly put it, this phenomenon borders on science fiction. It contradicts our established understanding of reproduction, the boundaries between species, and the principles of evolutionary progression. Yet, this is precisely what is currently happening within ant colonies across the European continent. The specific ant in question is Lasius neglectus, an invasive species that has proliferated throughout Europe over the past few decades. It inhabits what scientists refer to as supercolonies, extensive networks of interconnected nests that can span kilometers. These colonies exhibit no clear demarcation between individual nests, nor do their workers display aggression towards one another, regardless of their origin nest. Instead, they function as a single, massive cooperative society. This characteristic alone is quite unusual, as most ant species are fiercely territorial, with workers from different colonies frequently engaging in fatal combat. However, the workers of Lasius neglectus recognize each other as kin, even across considerable distances. Researchers have now made an even more astonishing discovery. The queens of this species are producing workers that are not their genetically direct offspring. This is not achieved through conventional reproduction, but rather through cloning, and importantly, not self-cloning. They are somehow producing clones of workers from a different species entirely, Lasius flavus, a related but distinct species. While the precise mechanism is still under investigation, genetic analysis unequivocally confirms that the workers within these colonies possess DNA matching Lasius flavus, not Lasius neglectus, despite being produced by Lasius neglectus queens. The prevailing hypothesis suggests the involvement of stolen eggs or larvae. It is theorized that the queens somehow acquire genetic material from the other species and utilize it to produce workers, potentially by hijacking reproductive cells or through an as-yet undocumented form of genetic parasitism. The resulting workers are fully functional. They exhibit typical worker ant behaviors, such as foraging, caring for the young, and defending the nest. Genetically, however, they belong to a different species. This is considered biologically impossible. Cloning within a species is a well-documented phenomenon in nature. Certain lizards, fish, and even some ant species reproduce via parthenogenesis, producing offspring without fertilization. However, interspecies cloning, where one organism generates genetic duplicates of another, fundamentally violates established biological principles. Except, evidently, it does not, because it is occurring. Evolution is indifferent to our predefined rules. Evolution prioritizes what proves effective. If a particular strategy enhances reproductive success, it will propagate. In some manner, the production of cloned workers from another species confers an advantage upon these Lasius neglectus queens. It is possible that these cloned workers are more adept at specific tasks, or perhaps they are more expendable. Alternatively, the genetic diversity they introduce might bolster the colony's resilience against diseases or parasites. The exact nature of this advantage remains unclear, but it must exist. Otherwise, this extraordinary strategy would not have evolved. The implications of this discovery extend far and wide. If ants are capable of such feats, what other organisms might be exhibiting similar phenomena? Are there other creatures blurring species boundaries in ways we have yet to observe? How many of our assumptions regarding reproduction and genetics are merely oversimplifications? Biology is inherently complex and nuanced. The more we investigate, the more exceptions we uncover to the rules we once believed to be universal. Certain species of magic mushrooms have independently evolved the capacity to produce psilocybin through entirely distinct biochemical pathways, a discovery made through genomic analysis of various psilocybin-producing mushroom species. The genes involved in these two separate evolutionary events are unrelated and do not share a common ancestry. This indicates that two distinct groups of mushrooms independently devised methods for synthesizing the same molecule using different chemical processes. This is a prime example of convergent evolution at the molecular level, akin to how wings evolved independently in insects, birds, and bats, or how eyes developed separately in vertebrates and cephalopods. Such instances involve analogous solutions arising to similar challenges through divergent evolutionary routes. However, convergent evolution of a complex molecule is a rare occurrence. Molecules are specific in nature, requiring precise enzymes to catalyze each stage of their synthesis. The fact that multiple mushroom lineages independently developed complete biosynthetic pathways for psilocybin strongly suggests that psilocybin confers a significant evolutionary benefit. What might this advantage be? Mushrooms produce psilocybin in their fruiting bodies, the parts visible above ground that are often consumed by animals. Psilocybin has a notable effect on animal behavior, inducing altered perceptions, mood changes, and sometimes aversion. It is plausible that this deters herbivores, leading them to avoid consuming the mushroom after experiencing a strange or unpleasant sensation. Another possibility is that it attracts specific animals that aid in spore dispersal. By consuming the mushroom and experiencing a vivid trip, these animals might be more inclined to remember and share the location, thereby increasing spore dissemination. While the exact reason is not definitively known, the strong evolutionary selection pressure favoring psilocybin production, leading to its independent evolution twice, underscores its importance to the mushroom's fitness. The molecule's interaction with human brains, resulting in profound psychological experiences, is coincidental. Humans did not exist as a selective pressure when mushrooms evolved psilocybin millions of years ago. However, the molecule happens to interact with serotonin receptors in mammalian brains. Our neurological structures are sufficiently similar to those of the animals that consumed these mushrooms for us to experience similar effects. Sperm bots, microscopic robotic devices capable of being navigated through reproductive tracts, have been developed and successfully tested in artificial cervices and uteri, demonstrating the feasibility of the concept. The primary objective is to advance fertility treatments by assisting sperm in reaching eggs when their natural motility is compromised. Male infertility often stems from sperm exhibiting impaired swimming ability, low motility, or abnormal morphology. While these sperm are genetically normal and viable, they are unable to complete the journey to fertilization. A sperm bot is a microscopic apparatus that attaches to a sperm cell, providing it with propulsion. Magnetic fields are employed to control and guide the bot through the reproductive tract directly to the egg. Upon reaching its destination, the bot detaches. The sperm then proceeds to fertilize the egg normally. The bot itself is inert, biocompatible, and eventually degrades or is naturally cleared by the body. In principle, the concept is elegant, but practical implementation presents challenges. These include navigating the intricate internal environment, ensuring the bot does not harm the sperm or surrounding tissues, and guaranteeing its timely release. Nevertheless, the proof of concept has been established, with sperm bots demonstrating functionality under controlled laboratory conditions. This is the type of innovation that initially sounds like science fiction until it is successfully realized. Subsequently, it transitions into a standard medical device, initially perceived as unusual, but eventually becoming routine. In 2 decades, if sperm bots become a commonplace fertility treatment, they will be regarded with the same normalcy as in vitro fertilization is today. IVF itself faced considerable controversy upon its inception, with concerns raised about playing God. It has since evolved into a multi-billion-dollar industry responsible for the creation of millions of lives. A vibrant orange shark, the first of its kind, has been discovered in the Caribbean. Orange coloration is exceptionally rare among sharks. Most exhibit gray, brown, or muted tones that provide camouflage. This particular shark, however, possesses a vivid orange hue, making it highly conspicuous. It also exhibits 2 rare genetic conditions: albinism, which eliminates pigmentation, and erythrism, which adds red pigment. The combination of these conditions results in its striking orange color. This shark is essentially a double mutant, managing to survive despite its conspicuous appearance in an environment where camouflage is typically crucial. Alternatively, it is possible that the orange coloration offers an unexpected advantage. Deep-sea sharks are less dependent on visual camouflage, as their prey often relies on sensing electrical fields or chemical cues for detection. In the deep ocean, being bright orange might be inconsequential, or it could even facilitate species recognition for purposes such as mating or social signaling. The precise reason is unknown. However, the fact that this shark survived to adulthood suggests that its orange coloration is not immediately detrimental. Occasionally, mutations that appear disadvantageous may prove to be neutral or even beneficial in specific contexts. A flower that emits the scent of dying ants has been identified. Vinca toxicum nakianum, a plant species, has evolved to mimic the chemical signals released by ants when they are attacked by spiders. The purpose of this mimicry is to attract flies. Flies are drawn to the aroma of dying ants, presumably because it signals a food source. Observing dead ants or evidence of spider predation. Flies that are seeking carrion or scavenging opportunities are drawn to investigate. While these flies are investigating the flower, they inadvertently pollinate it. From the fly's perspective, this is an accidental occurrence, but from the plant's perspective, it is a precisely orchestrated strategy by evolutionary processes. This represents a highly unusual form of deceptive pollination. Many plants employ deception to attract pollinators. Orchids, for example, resemble female insects, tricking male insects into attempting to mate with them, thereby picking up pollen in the process. Other flowers emit the odor of rotting meat to attract carrion flies. However, The specific mimicry of the chemical profile of ants under attack is exceptionally specialized. It necessitates the plant producing a blend of volatile compounds that precisely matches those emitted by ants. Furthermore, it requires that flies have learned to associate this particular scent with the availability of food. This entire system involves a complex, three-way interaction: ants, spiders, and flies, each operating according to their own biological imperatives. However, the plant has successfully inserted itself into this interaction, exploiting the behavioral response of the flies to its reproductive advantage. Dogs possess the cognitive ability to mentally categorize their toys based on their function. This goes beyond simply recognizing individual toys. They can group them into categories. This was demonstrated in studies where dogs were presented with multiple toys and instructed to retrieve specific ones. Some dogs exhibited the ability to generalize, understanding that all balls, for instance, share commonalities. This demonstrates abstract categorization, not merely memory recall or a response to learned names, but an understanding that objects belong to functional groups. This suggests a more sophisticated level of cognition in dogs than is typically attributed to them. They are not merely trainable or responsive to commands, but are capable of concept formation, of comprehending that objects can be grouped based on properties other than their appearance. A tennis ball and a rubber ball, while visually distinct, serve a similar function. A dog that grasps this is engaging in a cognitively complex behavior. It is constructing mental models that illustrate the relationships between objects. This ability likely extends to other domains. Dogs categorize people into groups such as family, strangers, threats, and friends. They categorize locations as safe, dangerous, or interesting. They also categorize behaviors as play, aggression, or submission. The study involving toys reveals that this categorization is not purely instinctual. It is a learned and flexible process. Dogs can establish new categories based on their experiences. This cognitive capacity is fundamental to complex social behavior, enabling them to live in groups, cooperate, and anticipate the actions of others. Dogs have evolved alongside humans for tens of thousands of years, and their brains have adapted to our social environment. Categorization plays a significant role in this adaptation. Bacteria present in human brains fluctuate in correlation with sleep cycles. This finding challenges the long-held notion that the brain is a sterile environment. For many decades, the prevailing assumption was that healthy brains are devoid of bacteria. The blood-brain barrier was believed to effectively prevent their entry. The presence of bacteria in the brain was historically associated with infection, such as meningitis and encephalitis, serious and potentially life-threatening conditions. However, recent research employing highly sensitive techniques has detected bacterial molecules within healthy brain tissue. Furthermore, the concentrations of these molecules vary with the sleep-wake cycles. This phenomenon is not indicative of an infection, but rather suggests a low-level presence of bacteria. It is possible that these bacteria reside in the vascular system near the brain, or perhaps metabolic byproducts from gut bacteria are crossing into the bloodstream and subsequently reaching the brain. The full implications of this discovery are still being elucidated. However, if bacterial molecules influence brain function and their presence fluctuates with circadian rhythms, it suggests an even more direct connection between the gut and the brain than previously understood. This implies that dietary intake and the composition of gut bacteria could directly impact brain chemistry in real time, not solely through nutrient absorption, but also through bacterial metabolites and molecular signaling. This could provide explanations for certain unexplained phenomena, such as the correlation between gut health and mental well-being, the cognitive side effects sometimes associated with antibiotic use, and the alterations in mood and cognition observed after fasting or dietary changes. The brain is not an isolated organ. It is an integral part of a larger system. This system includes the trillions of bacteria residing in the gut, which produce compounds that enter the bloodstream and reach the brain. Honeybees have been observed to utilize pollen as a form of medicine, not merely as a nutritional source. Pollen contains bacteria belonging to the Streptomyces genus. These bacteria produce antimicrobial compounds, essentially natural antibiotics. When bees collect pollen, they inadvertently gather these bacteria. The bacteria then colonize the beehive, producing compounds that help combat pathogens, including bee diseases, fungal infections, and even plant diseases that could contaminate stored pollen. While the bees do not intentionally cultivate these bacteria, they derive significant benefits from their presence. This represents a mutualistic relationship. The bacteria find a habitable environment within the hive, and the bees receive antimicrobial protection. Furthermore, this phenomenon illustrates horizontal gene transfer in action. While not direct genetic exchange, it represents an ecological integration where bees, bacteria, and flowers interact in ways that influence each other's evolutionary trajectories. Flowers that host beneficial bacteria, are visited more frequently by bees. Bees that tolerate and transport these bacteria experience improved health. Bacteria that produce compounds beneficial to bees proliferate. Over successive generations, this symbiotic system co-evolves, with each partner adapting to the presence of the others. The venom of the black mamba possesses a concealed characteristic that sheds light on why antivenoms occasionally prove ineffective. Mambas are among the most perilous snake species, known for their speed, aggression, and potent venom. Their venom is a complex mixture of neurotoxins, proteins that disrupt the nervous system by blocking signals, leading to paralysis and, ultimately, respiratory failure. Antivenom functions by neutralizing these toxins through antibodies that bind to venom proteins, preventing them from reaching their targets. However, in some instances, antivenom treatment is unsuccessful and victims succumb. Recent research has revealed that the venom employs a dual attack mechanism. The initial assault consists of neurotoxins, previously understood, which cause rapid, flaccid paralysis. Antivenom is effective against these. However, a second wave of toxins, composed of different proteins, acts more slowly and induces a distinct type of paralysis, described as spastic. Crucially, the antivenom does not target these second-wave proteins. Consequently, even if the initial toxins are neutralized, the second wave can still prove fatal. This discovery explains the failures observed in antivenom treatments. It also necessitates a reformulation of antivenoms to target both sets of proteins, thereby providing comprehensive protection against the full spectrum of black mamba venom. This principle applies to many venoms. They are complex mixtures that are constantly evolving. Snakes with more sophisticated venoms tend to be more successful predators. Prey that survive exposure to one type of toxin may still succumb to another. This represents an evolutionary arms race, where venom becomes increasingly complex and prey develops greater resistance, prompting further venom adaptation. We observe snapshots of this ongoing process. The black mamba's venom, with its dual mechanism, is one such example. It serves as a reminder that biological systems are invariably more intricate than our current understanding allows. September 2025. European ants exhibiting the ability to clone members of different species. Magic mushrooms independently evolving psilocybin through disparate pathways. Sperm bots navigating artificial reproductive systems. Orange sharks surviving despite possessing two genetic abnormalities. Flowers mimicking the scent of dying ants to attract pollinating flies. Dogs demonstrating the capacity to mentally categorize toys based on their function. Bacteria detected in healthy human brains, with their presence fluctuating alongside sleep patterns. Honeybees utilizing bacteria present in pollen as a form of natural antimicrobial defense. Black mamba venom exhibiting hidden mechanisms that render antivenoms ineffective. Each discovery functions as a crucial piece of a larger puzzle, filling in knowledge gaps, revealing interconnectedness, and demonstrating that life is far more extraordinary and inventive than we previously imagined. Evolution does not adhere to our preconceived notions. It devises solutions that we could not have predicted. It transcends boundaries that we believe to be immutable. It generates relationships, mechanisms, and strategies that appear impossible until they are documented. At that point, they are simply recognized as biological phenomena, representing yet another manifestation of what 4 billion years of evolution can produce when selective pressures interact with genetic variation over immense geological timescales. The rules we learn in academic settings are typically generalizations, valuable for comprehending common scenarios, but nature is replete with exceptions, and these exceptions often represent the most captivating aspects. Chapter 10. Technology that evokes science fiction. 100 gigabits per second. This represents a speed 10,000 times faster than 5G. 10,000. Not a 10% increase, not even double the speed, but 10,000 times faster. This is the performance capability of the new 6G chip. It possesses full-spectrum capability, enabling transmission and reception across the entire electromagnetic spectrum allocated for wireless communication. The ramifications of this advancement are profound. Imagine downloading a full-length 4-kilobyte movie in mere moments. Envision streaming multiple high-definition video feeds concurrently without any perceptible delay. Consider the ability to connect thousands of devices in densely populated areas without experiencing network congestion. This is not a mere incremental enhancement. It is a fundamental paradigm shift in wireless technology. While 5G was heralded as transformative and has indeed proven so, in specific applications such as industrial automation, remote surgery, and autonomous vehicles, for the majority of consumers, 5G has felt like little more than a slightly faster version of 4G. The truly revolutionary applications have yet to fully materialize, partly due to incomplete infrastructure, partly because developing applications for novel capabilities requires time, but predominantly because 5G, while faster than 4G, has not offered a sufficient degree of difference to enable entirely new use cases. 6G, however, is sufficiently different. At 100 gigabits per second, bandwidth ceases to be a limiting factor. Latency is reduced to near zero, measured in mere milliseconds, rendering it almost instantaneous. This opens the door to capabilities that are currently unattainable. True holographic communication, transcending video calls to project three-dimensional representations of individuals in real time. Virtual reality experiences that are indistinguishable from physical presence. Augmented reality overlays with no perceptible delay. Brain-computer interfaces capable of wirelessly streaming neural data. Medical sensors providing continuous, high-resolution monitoring. Autonomous systems that can coordinate in real time across vast distances. The innovation revolves around silicon photonics, a field that harnesses light rather than electrical currents for data transmission. Photons possess superior speed and information-carrying capacity compared to electrons. Silicon photonics facilitates the integration of optical components directly onto silicon chips. Remarkably, the same sophisticated manufacturing methods employed for conventional computer processors can be utilized to produce photonic chips. This technological convergence promises remarkable scalability and mass production capabilities, leading to a reduction in costs as production volume escalates. While initial 6G chips are projected to be costly, historical trends in semiconductor development suggest that they will become affordable and widely accessible within a decade, mirroring the trajectory of previous semiconductor advancements. China is currently spearheading the effort to implement 6G technology, recognizing its profound strategic importance. The nation that commands the next generation of wireless infrastructure will inevitably dictate the digital economy, establish global standards, secure vital patents, and control equipment manufacturing. China aspires to replicate the preeminence the United States held during prior wireless technology generations. Consequently, significant investments are being channeled into building experimental networks, filing patent applications, and developing innovative applications. The ambitious objective is to have commercial 6G networks fully operational by the year 2030, a mere 5 years from now. In contrast, the United States and Europe appear to be lagging, finding themselves in a familiar position of playing catch-up. Meanwhile, within the medical domain, researchers have engineered a groundbreaking bone grafting adhesive applicator. This device is capable of three-dimensionally fabricating bone material directly onto fracture sites, bypassing the need for external supports, metal plates, or screws, and instead creating actual bone, or more precisely, a biological scaffold that bone cells can colonize and transform into genuine bone tissue. The applicator dispenses a biocompatible paste composed of calcium phosphate, collagen, and growth factors. This paste rapidly solidifies within minutes, effectively stabilizing the fracture. Subsequently, over a period of weeks, osteoblasts, the cells responsible for bone formation, migrate into the scaffold. These cells deposit new bone matrix, gradually degrading the scaffold, which is ultimately replaced by living bone. This innovation addresses a significant challenge in orthopedics, particularly for fractures in difficult locations, complex breaks, and bones that exhibit poor healing potential. Current surgical practices often involve the implantation of metallic hardware, such as plates and screws. While effective, these are permanent foreign bodies that can cause discomfort, interfere with medical imaging, and occasionally necessitate removal through a secondary surgical procedure. Bone grafting offers an alternative, involving the transplantation of bone from another part of the patient's body or from a donor. However, this method is subject to limitations concerning graft availability, donor site morbidity, and the potential for rejection or infection. The development of a printable bone scaffold elegantly circumvents these drawbacks. The constituent material is biocompatible and seamlessly integrates with the patient's own bone tissue, eliminating the need for subsequent removal. The precise application afforded by the adhesive applicator is a crucial advantage. Surgeons can meticulously deposit the material, layer by layer, constructing three-dimensional structures that precisely conform to the patient's anatomy, effectively filling voids and bridging gaps. The material's consistency is akin to toothpaste, sufficiently firm to maintain its shape, yet pliable enough for smooth extrusion. Preclinical trials in animals have yielded promising results, and human trials are now commencing. Should these trials confirm the safety and efficacy of this technology, it is poised to become a standard instrument in operating rooms, ushering in an era of faster, less invasive, and more effective fracture repair. Quantum computing is currently yielding technological advancements that defy conventional understanding. One such development is a cryogenic device capable of reducing heat emissions by a factor of 10,000. Quantum computers necessitate operation at temperatures approaching absolute zero, mere millikelvin. This extreme cold demands sophisticated refrigeration systems, including dilution refrigerators and cryogenic apparatus designed to actively remove heat. Paradoxically, these very cooling systems generate heat themselves through compressors, pumps, and electronic components, which must be dissipated. In most environments, this excess heat is radiated into the surroundings. However, in the vacuum of space, heat radiation is an inefficient process, as there is no atmosphere for convection. This poses a significant challenge for quantum satellites, space-based quantum communication networks, and quantum sensors deployed in orbit, all of which rely on quantum computers for their operation. Maintaining the cryogenic temperatures required for quantum computers in the harsh environment of space presents a formidable obstacle. The newly developed cryogenic device employs advanced materials and an innovative geometric design to more efficiently channel heat. This results in a 4 orders of magnitude reduction in thermal load, meaning 10,000 times less heat needs to be dissipated. This breakthrough renders space-based quantum systems eminently practical, enabling the maintenance of the precise temperatures essential for quantum coherence without the need for cumbersome refrigeration machinery. The device is compact, consumes minimal power, and is slated for deployment on a test satellite in the year 2026. Its successful operation will unlock a plethora of quantum applications in space, including unhackable quantum communication between satellites, secured by the principles of quantum entanglement, where any attempt at interception disrupts the entanglement and instantly alerts to eavesdropping. Furthermore, it will enable the development of highly sensitive quantum sensors capable of detecting gravitational waves, magnetic fields, and other phenomena with unprecedented accuracy. The advent of space-based quantum computing will also expand the scope of applications requiring computational power that currently exceeds terrestrial capabilities. While these applications may not be immediate, they are on the foreseeable horizon, and this innovative cryogenic device represents a pivotal enabling technology. Advances in brain-computer interfaces are progressing at a pace that outstrips general awareness. Artificial intelligence can now predict the likelihood of recovery from spinal cord injuries by analyzing routine blood tests. The predictive power lies in subtle patterns formed by combinations of biomarkers, which correlate with neural regeneration processes, inflammatory markers, growth factors, immune cell counts, and metabolic indicators. Individually, these markers offer limited predictive value. However, machine learning algorithms are adept at identifying the crucial combinations that hold predictive significance. By training these algorithms on the outcomes of thousands of patients, they learn to discern patterns associated with recovery versus those indicative of permanent impairment. This capability extends beyond academic interest. It has the potential to fundamentally alter treatment decisions. If a blood test predicts a poor recovery prognosis, pursuing aggressive interventions, such as experimental therapies, surgical procedures, and intensive rehabilitation, becomes a rational course of action. Conversely, a prediction of good recovery might favor a more conservative management approach, avoiding unnecessary risks and allowing natural healing processes to unfold. Presently, medical professionals base these critical decisions on the nature of the injury itself, its location, severity, and imaging findings. However, these factors do not always correlate reliably with eventual outcomes. Two individuals with ostensibly similar injuries can experience vastly different recovery trajectories. The inclusion of blood biomarker data introduces an additional layer of information, leading to more accurate predictions and, consequently, improved treatment choices. Moreover, blood tests are cost-effective, routinely performed, and already integrated into standard medical care. This eliminates the need for novel equipment or specialized facilities. Samples can be sent to a laboratory for analysis, yielding actionable results. Upon validation and regulatory approval, the AI model will become a standard diagnostic tool. Every spinal cord injury patient would undergo this blood test, with the algorithm generating a prognosis to guide physicians in their treatment strategies. Over time, this personalized approach to treatment is expected to enhance patient outcomes. Apple is undertaking a significant redesign of its iPhone architecture, prioritizing an AI-first operational framework. Current iPhone models feature discrete chips, the Central Processing Unit, CPU, Graphics Processing Unit, GPU, and Neural Engine, each specialized for different tasks. The CPU handles general computations, the GPU renders visual graphics, and the Neural Engine executes machine learning models. However, as artificial intelligence becomes increasingly integral to every facet of smartphone functionality, this segregation introduces inefficiencies. Data must constantly transfer between these separate chips, consuming time and power, leading to increased latency and accelerated battery drain. The proposed redesign involves a unified chip architecture, integrating AI acceleration capabilities into every component. The CPU will incorporate AI-optimized cores, the GPU will include dedicated neural processing units, and the memory system will be engineered to support high-bandwidth AI workloads. This holistic, co-designed approach, centered around machine learning, will enable significantly faster and more efficient on-device AI processing. Capabilities such as voice recognition, image processing, real-time translation, and predictive text will all be executed locally, eliminating the need to transmit data to the cloud, thus eradicating latency and addressing privacy concerns associated with data leaving the device. Furthermore, enhanced efficiency will translate to improved battery life. This strategic move represents Apple's response to the ongoing AI revolution. While competitors like Google and Microsoft rely on cloud-based AI solutions, which are powerful but contingent on connectivity, Apple aims to champion local AI, ensuring all operations occur on the device itself, irrespective of internet access. This aligns perfectly with Apple's privacy-centric brand identity and strategically positions the company for a future where AI is ubiquitous, with every application and interaction leveraging machine learning. The iPhone is evolving from a mere device to a sophisticated intelligent assistant that anticipates user needs, offering contextual, adaptive, and personalized experiences. Materials for wetsuits that substantially mitigate the severity of shark attack injuries are emerging from rigorous testing conducted by shark researchers. Four distinct materials have been developed, each engineered to resist shark bites rather than prevent them entirely, which is deemed an unachievable objective. However, these materials are designed to reduce the extent of injuries, distribute impact forces, prevent deep penetration of teeth, and minimize blood loss. In controlled experiments involving actual sharks, these materials demonstrated a significant reduction in trauma compared to conventional neoprene. This development holds considerable importance as shark attacks, though statistically infrequent, are on an upward trend, coinciding with increased human presence in marine environments for activities like surfing, diving, and swimming. Sharks, by their nature, engage in their own behaviors. Most shark encounters are not predatory, but rather investigative, often stemming from mistaken identity. Nevertheless, even these investigative bites can result in severe injuries, substantial blood loss, tissue damage, and, in unfortunate instances, fatalities. Enhanced protective gear has the potential to save lives by reducing injury severity, even if it cannot eliminate risk entirely. The materials in question are multi-layered. Outer layers are designed to resist abrasion and cutting, while inner layers absorb impact energy. Some incorporate rigid plates to deflect teeth, while others utilize ultra-high molecular weight fibers renowned for their cut resistance. The ultimate goal is to produce wetsuits that offer substantial protection while maintaining a comfortable, normal feel. Surfers and divers are unlikely to adopt bulky, armor-like gear, but they would readily embrace a wetsuit that looks and feels standard yet is engineered for bite resistance. Widespread adoption of these materials could lead to a reduction in shark attack fatalities, not through fewer attacks, but through improved outcomes when attacks do occur. Biotar, a problematic byproduct of biomass gasification, is now being repurposed for clean energy production and carbon capture. Biomass gasification involves heating organic matter in low oxygen conditions, resulting in the breakdown into gaseous, liquid, and solid components. The gases can be combusted for energy, the liquids yield bio-oils, and the solids form biochar. However, a sticky, toxic, and challenging to handle residue known as biotar is also generated. Historically, biotar has been considered waste, disposed of, or burned inefficiently, presenting a persistent problem with no easy solution. A novel technology has been developed to convert biotar into biocarbons, a material analogous to activated charcoal. This biocarbon material possesses a large surface area and a porous structure, making it valuable for filtration, catalysis, and carbon sequestration. The conversion process involves carefully controlled pyrolysis. During this process, the biotar breaks down further, its toxic compounds volatilizing and being either captured or cleanly combusted. The remaining substance is stable carbon. This stable carbon can be utilized in industrial applications, sequestered as a carbon sink, or incorporated into soil as an amendment, effectively transforming what was once waste into a valuable product. This innovation elevates biomass gasification from a marginally viable technology to a robust and economically sound one. The economic feasibility is enhanced when every output from the process has intrinsic value. Furthermore, the environmental impact is significantly improved as toxic waste is transformed into a useful material and contributes to carbon sequestration. The carbon present in biotar originates from plants, which absorb it from the atmosphere. By converting this atmospheric carbon into stable biocarbon and sequestering it, or using it in long-term applications, that carbon is effectively locked away. While not a complete panacea for climate change, this process represents a valuable component. offering a method to remove carbon dioxide from the atmospheric cycle while simultaneously producing beneficial materials and energy. Underground electron pathways are revolutionizing the cleanup of environmental pollutants. For many years, the prevailing understanding was that soil microbes were responsible for breaking down pollutants solely in their immediate vicinity. Degradation occurred where microbial populations were present, and pollutants persisted where they were absent. However, recent research has revealed that electrons can traverse soil over considerable distances. This is facilitated by naturally occurring conductive networks formed by minerals, organic molecules, and specialized bacteria. Electrons generated by microbes in one location can travel through these networks, extending for meters, to reach and neutralize pollutants situated elsewhere. The pollutants are then reduced and broken down by electrons originating from a distant source. This discovery fundamentally alters the approach to bioremediation. Instead of requiring microbial presence at every contaminated spot, contaminated sites now benefit from the establishment of conductive networks and the flow of electrons. If these networks can be established and maintained, the cleanup process can effectively spread. This can be achieved through deliberate engineering, such as introducing minerals that enhance electron conductivity, cultivating bacteria that form conductive filaments, or increasing the organic matter content of the soil. The soil then functions as an electrical grid, with electrons acting as the agents of cleanup. Pollutants located anywhere within this grid are degraded by electrons that migrate through the system. This finding also suggests that natural attenuation, the process by which contamination diminishes over time without active intervention, is more potent than previously understood. Electron flow may be contributing to pollution cleanup in ways that have gone undetected. Sites previously deemed persistently contaminated might, in reality, be slowly healing through this underground electron transfer mechanism. This does not imply that pollution can be disregarded. Rather, it indicates that nature possesses more sophisticated mechanisms for addressing contamination than current models account for. Water confined within nano-sized channels enters a peculiar pre-melting state, exhibiting characteristics of both solid and liquid simultaneously. This phenomenon has been observed through advanced nuclear magnetic resonance studies. When water molecules are restricted to spaces only a few nanometers wide, narrower than the dimensions of a virus, they exhibit unusual behavior. Instead of freezing or melting at a sharp, defined temperature, water in these confined spaces displays a transitional temperature range where it possesses partial ordering, akin to ice, and partial disorder, characteristic of a liquid. Both states coexist, with individual molecules flickering between them. The system, therefore, exists in an intermediate state, neither purely solid nor purely liquid. This finding has significant implications for understanding water's behavior within biological systems. Cells are replete with nano-sized environments, including water confined between cellular membranes, within protein channels, and throughout the crowded intracellular space. This confined water does not behave like bulk water. Its properties are altered. These alterations can influence protein folding, membrane function, and the cellular regulation of the internal environment. Comprehending these pre-melting states is crucial for explaining biological phenomena that cannot be adequately addressed by considering the properties of bulk water alone, such as supercooling, glassy states, and anomalous diffusion. Life's evolution has likely capitalized on these distinct properties of confined water. Cosmological simulations that once demanded the power of supercomputers can now be executed on standard laptops through emulation. This involves creating fast approximations rather than full-scale simulations. Researchers have trained machine learning models using the output data from detailed cosmological simulations. These trained models acquire the ability to learn patterns related to galaxy formation, structural evolution, and dark matter clustering. Once trained, these models can rapidly generate outputs that closely resemble those of the original, computationally intensive simulations. Consequently, processes that previously took weeks on a supercomputer can now be completed in mere minutes on a conventional laptop. This advancement democratizes the field of cosmology, enabling graduate students to explore parameter spaces, test hypotheses, and iterate on ideas with unprecedented speed, without the need for lengthy waits for supercomputer allocation. Furthermore, it removes the institutional barrier, allowing individuals at any institution with access to a decent laptop to engage in sophisticated cosmological modeling. While the fidelity of emulators is not absolute, and they involve approximations, they are sufficiently accurate for many research purposes and are continuously improving. Each successive generation of emulators incorporates more physics and resolves finer details, progressively narrowing the gap in accuracy between emulators and full simulations. This demonstrates the transformative power of applying machine learning to scientific computation. The process of training computationally inexpensive emulators on the results of costly simulations allows for the capture of complex patterns without the necessity of solving every underlying equation. This approach is applicable to a wide range of scientific disciplines, including climate modeling, fluid dynamics, and material science, in any field where computational models are too time-consuming for extensive exploration. The strategy involves training an emulator for rapid exploration, followed by validation of key findings using full-scale simulations. This hybrid methodology accelerates the pace of scientific discovery by enabling a greater number of scientists to participate in a wider array of ideas to be tested, thus increasing the overall velocity of research. September of the year 2025 marks a significant milestone with the anticipated transmission speeds of 6G chips reaching 100 gigabits per second. Simultaneously, advancements in medical technology will include bone grafting adhesive applicators capable of printing living bone, and cryogenic devices that reduce heat emissions from quantum computers by a factor of 10,000. In artificial intelligence, algorithms will predict spinal cord injury recovery based on blood tests. Apple is set to unveil redesigned iPhones with an AI-centric architecture. Wetsuit materials engineered to diminish the severity of shark bites are emerging. Biotar, a problematic industrial byproduct, will be transformed into valuable biocarbons, and underground electron pathways will revolutionize pollution cleanup. Water confined within nano-sized channels will exhibit a simultaneous solid and liquid state. Cosmological simulations will be accessible on laptops through machine learning emulation. Each of these breakthroughs represents a new tool, and each tool paves the way for novel applications. Consequently, the realm of what is possible is continuously expanding, and the rate of this expansion is accelerating not linearly, but exponentially. Technologies are building upon other technologies, and discoveries are enabling further discoveries. The pace is breathtaking, and the implications are profound. We are still in the nascent stages of comprehending the full potential of these emergent tools,